Hey everyone. Tonight, we fall gently into the fabric of the cosmos, where gravity folds reality and silence has weight. You're lying beneath a sky that doesn't blink, surrounded by stillness so deep it hums. There are no clocks here, no noise, just you and the voice of the star. As we drift into the mystery Stephen Hawking spent his life unraveling, tell me this in the comments. What time is it where you are, and what city are you falling asleep in? I'll meet you at the event horizon. Now close your eyes and listen. There's a kind of silence found only in space, not quiet but a vast, indifferent stillness. And within that stillness lies a question: what happens when gravity becomes absolute? A black hole, not a hole, not black, but a region where light cannot return, and the laws of physics turn inward. Stephen Hawking didn't discover black holes, he made them meaningful. He asked what no one else had asked: what happens at the edge? Long before that, he was a student, learning how time could bend. When he was diagnosed with ALS at 21, he began to think more deeply about endings, not just his own, but the universe's. It wasn't morbid, it was curiosity sharpened by urgency. Imagine a star, massive, glowing. At the end of its life it collapses inward. No explosion, just implosion. It folds into a singularity, a point where density is infinite, and time stops. This is where Hawking began. Working with Roger Penrose, he showed that singularities aren't rare, they're expected outcomes of Einstein's equations. Collapse enough matter, and space itself curves to a point. If this happened in the center of a black hole, it could have also happened at the origin of the universe. The Big Bang, then, was not an explosion, but a singularity expanding. Time began there. Before that, before meant nothing. Hawking didn't stop with beginnings. He asked what happens after. What does a black hole do over time? Does it last forever? Or does it fade? In 1974, Hawking proposed that black holes emit radiation, not because they want to, but because quantum mechanics demands it. At the edge of a black hole, pairs of particles appear. This happens everywhere in space. Particles flicker into existence, then cancel out. But if one particle falls into the black hole, while the other escapes, it looks like the black hole is glowing. This became known as Hawking radiation. It meant black holes lose energy, and eventually, disappear. But what about the information they consume? Quantum mechanics says information can't be destroyed. General relativity doesn't seem to agree. This contradiction became the black hole information paradox. Hawking's ideas forced science to confront this divide. He believed information was lost, then changed his mind. Maybe the information clings to the event horizon, encoded in ways we haven't yet understood. Later theories suggested the horizon itself might be a kind of hologram, a skin where the history of everything that falls in is somehow written. This wasn't just physics. It was storytelling, and Hawking told it in a way no one had before. Though he couldn't speak without a machine, his ideas reached farther than most voices. He debated the nature of reality with a cheek muscle and a voice synthesizer, and won. He didn't romanticize science. He explained it. He made people see that the edge of a black hole was not the end of understanding, but the beginning of a deeper question. Look up at the stars, he said. Don't waste time on fear. Understand what's possible. Even if you are confined to a chair, your thoughts can move through time. Stephen Hawking didn't make the stars. He taught us how to listen to them. And what he heard was astonishing. He heard time twisting, space stretching, rules breaking down at the edge of understanding. He didn't settle for beauty. He wanted truth, and if the truth was stranger than fiction. Let's pause for a moment on gravity. Gravity pulls, but in Einstein's universe, gravity doesn't pull like a string. It curves. It tells matter how to move by shaping the space it lives in. Edging a stretched sheet, place a ball on it. The sheet dips. Roll a smaller ball nearby. It spirals in. That's gravity. Not a force, but a bending of the stage beneath our feet. Now imagine that bend becomes so steep, so deep, it breaks through. That's a black hole. Hawking didn't just look at black holes, he asked what they meant. And what they meant was disturbing. A black hole doesn't let light out. It swallows time. Its center, the singularity, is a point of infinite density. That's not just dense, it's a breakdown of physics. When you divide anything by zero, you get nonsense. A singularity is that kind of nonsense brought to life. And yet, they exist. The universe permits them. Not rarely. Inevitably, massive stars end in singularities, and perhaps the entire universe began with one. Hawking's work with Penrose proved that under general relativity, a universe expanding today must have come from a singular point. That singularity wasn't in space. It was space. It wasn't in time. It was the beginning of time. There was no before. That idea alone would define Hawking's career. But he wasn't finished. He realized something even bolder. If the universe has a beginning, can we describe it without a boundary? In the 1980s, he proposed the no-boundary model. In simple terms, time may not have had a sharp start. It may have faded in the way a globe has no edge. Only smooth curves. Imagine standing at the South Pole. Which way is south? There is no south. There's no edge to fall off. That's what Hawking suggested about time. It just emerges. This wasn't just theoretical elegance. It was a challenge to how we imagine beginnings. A universe without a creator. A cosmos with no divine spark. Just laws, probabilities, and evolution. Hawking never denied wonder. He embraced it. But his wonder came from structure, not myth. He said, "It is not necessary to invoke God to light the blue touch paper and set the universe going." A bold claim, not anti-spiritual, just grounded in what the math showed. And behind the math was always the paradox. Hawking's great struggle was the same as everyone in theoretical physics, to reconcile relativity with quantum mechanics. One is smooth, the other is jittery. One describes planets, the other describes particles, and they don't like each other. Black holes sit at the crossroads. They are the only places where quantum uncertainty and gravitational certainty both demand attention. That's why Hawking radiation mattered so much. It was a quantum process in a gravitational setting. The first glimpse of a unified language. He never found that final language. No one has, but he walked closer than most. And he left behind equations, ideas, and contradictions that still define the work of others today. So when we speak of Stephen Hawking, it's not only about black holes, or entropy, or radiation. It's about the human ability to press against the unknown and make it speak. He made the universe feel personal. He made silence feel rich. He made gravity feel beautiful. And above all, he made complexity feel like an invitation. A voice among stars whispering, "Come close." The deeper you follow gravity, the more it begins to resemble thought. Not a force with hands or teeth, but a shape, a curve in the map of reality. Somewhere in that curve, tucked into its sharpest bend, lies the singularity. It is not an object, not a place you can visit. It's a limit, the edge of understanding, a mathematical warning sign where distance collapses, time fragments, and density rises without bound. It is the moment where Einstein's equations, so precise and powerful elsewhere, return only infinity. Stephen Hawking didn't invent singularities, but he followed them. He chased them to their source, to the beginning of time itself. Most of us imagine the Big Bang as an explosion, but that's a misunderstanding born from human scale. There was no blast, no sparks, no flames. There was a beginning, but it wasn't in space. It was space. It wasn't in time. It was time. Hawking's early work showed that under general relativity, if you trace the expansion of the universe backward, you reach a point, not just of compression, but of breakdown. Not only are particles crowded together, they no longer have separation. They lose identity. All things become one point, and that point has no size, no dimension, no past. It is a singularity. He wasn't the first to suspect it. Einstein's own equations hinted at the possibility, but Einstein doubted them. He believed nature would find a way to prevent collapse, that the universe abhorred infinities. But Hawking, with Penrose, proved otherwise. If certain reasonable conditions are met, gravity attractive, mass positive, energy conserved, then singularities are not just possible, they are required. That was radical, because it meant the laws of physics, the tools we use to explain everything else, lead us to a place where they stop working. And it didn't only apply to black holes, it applied to the universe itself, the expanding cosmos, measured in redshifts and background radiation. as a starting point, a moment where time becomes a line instead of a blur. But what kind of moment? What was the beginning? That question haunted Hawking. He believed science could answer it, if not with certainty, then with elegance. In the 1980s, he proposed a new way of thinking, the no-boundary condition. Imagine time not as a straight line, but as a curve that closes on itself. Not a circle, but a smooth, finite surface with no edge. Think of the Earth. You can walk north until you reach the North Pole. Beyond that, there is no north. It doesn't end. It curves. There's no border. Just geometry. What if time began like that? What if the Big Bang wasn't a singular spike, but a soft slope, where quantum fluctuations transitioned into classical space? In this model, time itself becomes imaginary. Not in the fictional sense, but in the mathematical one. Rotated 90 degrees in the complex plane, like a wave becoming a spiral. A beginning without a boundary. No need for divine intervention. No need for an edge. It was controversial. Some physicists admired the creativity. Others dismissed it as speculative. But Hawking didn't mind. He wasn't trying to write scripture. He was following the logic as far as it would go. And this was as far as it had ever gone. The universe, he said, would be completely self-contained. No need to appeal to anything beyond itself. It would simply exist, unfolding, expanding, its future written in its geometry. This doesn't mean the Big Bang didn't happen. It means it may not have been a bang at all. It may have been a bloom, a quantum seed swelling into space-time, a transition from probability to presence. And in that bloom, all the laws of physics were born. Gravity, electromagnetism, the strong and weak nuclear forces, all wrapped into one field that fractured as the universe cooled. That cooling created structure, structure created stars, stars forged heavier elements, explosions scattered them, planets condensed, life appeared, and none of it, not a single moment, was separate from that beginning. Singularities were not mistakes. They were the roots. But the roots still puzzle us. Hawking didn't stop at the where and when. He asked why. Why does the universe have the properties it does? Why these laws? These constants, this shape? He turned to the anthropic principle. The idea that the universe must allow observers like us, because we're here to observe it. Not a circular logic, but a recognition. The cosmos looks the way it does, because if it didn't, we wouldn't be around to wonder. That disturbed some scientists. It felt too philosophical, too convenient. But Hawking embraced the possibility that our universe might be one of many. A bubble, in a cosmic foam, each bubble with different laws, different constants, different outcomes. In most, life would be impossible. But in a few, maybe just one, conditions would align. Stars would shine, carbon would form, minds would emerge, and one day, a voice synthesized through a computer would ask how it all began. That's what singularities mean now. Not just death or collapse, but birth. A place where known physics gives way to something deeper, something still unnamed. Hawking believed that by studying these edges, we weren't just doing science, we were glimpsing the architecture of reality. Not chaos, but design. Not purpose imposed from outside, but order rising from the rules themselves. You once said, if we do discover a complete theory, it should be understandable by everyone, not just scientists. Then we shall all, philosophers, scientists, and just ordinary people, be able to take part in the discussion of why we and the universe exist. A complete theory, not to control the universe, but to understand it. That was the goal. And for Hawking, singularities were the first clue, the place where all answers must begin, and where all certainty ends. The Hawking-Penrose Theorems. To understand collapse is to understand creation. The universe does not begin with balance. It begins with instability, with too much density, with too much energy for space to hold. And in that imbalance, everything we know is born. Stephen Hawking's career turned on a single idea. The structure of space-time breaks, and in its breaking, something deeper is revealed. In the years after Einstein, relativity had become a masterpiece of explanation. It described how planets curved around suns, how time slowed in gravity's grip, how starlight bent near mass. It made the cosmos into a woven fabric, soft and vast, flexible under the weight of matter. But inside the equations lurked something darker. a prediction so extreme it felt absurd. If a massive star exhausted its fuel, its pressure would collapse, gravity would win, and if that collapse passed a certain point, nothing, not even light, could escape. And not only that, but the core would shrink endlessly, toward zero volume, toward infinite density, toward a singularity. Physicists were skeptical, not about the equations but about whether the universe would really allow it. Singularities, they thought, were signs that something had gone wrong in the math, that nature would step in, soften the collapse, and restore order. Then came Roger Penrose. He approached the problem not with particles, but with geometry. He showed that if mass were trapped in a small enough region, curvature would become unstoppable. He introduced the idea of a trapped surface, a closed boundary where light can move inward, but never outward. Once matter crossed that boundary, collapse was inevitable. A singularity would form. It was revolutionary. No longer was a singularity a strange corner case. It was the natural result of general relativity. Stephen Hawking read Penrose's paper in 1965. He was young, just beginning to develop his voice in cosmology. He was also living under the shadow of his diagnosis. His body was beginning to falter, but his mind was accelerating. Penrose's method offered Hawking something new, a way to explore the origin of the universe without relying on guesses, a path forward grounded not in equations alone, but in logical necessity. If singularities must form when things collapse, what happens if we reverse the direction? What happens when we follow time backward, not into stars, but into everything? Hawking turned Penrose's theorem inside out. Instead of applying it to the death of stars, he applied it to the birth of the universe. What he found was staggering. If the universe is expanding now, then it must have once been denser, and if you keep tracing that expansion backward, you find a past so tightly packed that even light could not move forward. Trapped surfaces everywhere, curvature without escape. The early universe was not just hot and dense, it was collapsed. Curved to a point, a singularity. This meant the Big Bang wasn't just a convenient model. It was required. If general relativity holds, and energy is positive, and the universe expands today, then it must have come from a singularity. Hawking's work in collaboration with Penrose became a collection of theorems, powerful, austere, and deeply unsettling. They said, in essence, that under broad and reasonable conditions, space-time cannot be complete. There will always be a boundary, a point where the equations break, a place where the fabric ends. Then this wasn't just about the past, it applied equally to the future. If enough mass collapses today, if a black hole forms, then its center too must contain a singularity. It wasn't a question of complexity, it was a question of inevitability. Singularities were no longer options, they were outcomes. Not just in exotic scenarios, but in the normal evolution of the cosmos. This shocked the physics community. It wasn't a hidden feature, it was a design, written into the rules of space-time itself. Yet these theorems did not describe what singularities are. They described that they must be. They didn't offer a picture of what happens inside. They didn't explain what replaces time when time reaches its end. They only said that the end comes, and that, for Hawking, was the most important clue of all. It meant general relativity, beautiful and powerful though it was, had limits. It could not explain its own boundaries. It could describe collapse, but not what lay beyond it. In black holes, and in the origin of time, there were gaps, places the math couldn't follow. And wherever the math ends, discovery begins. This opened the door to quantum gravity, to the need for a theory that could speak the language of both scales, the large and the small, the smooth and the jagged, the star and the atom. But before any such theory could be built, the theorems were essential. They were the roadmap. They told physicists where their current ideas could not reach. And they did so with devastating clarity. They needed no assumptions about symmetry, no fine-tuned conditions, just a handful of general truths. Gravity attracts, energy exists, light follows a predictable path, from those a singularity follows. To the outsider, it might seem like a dark message. Everything ends. All curves converge. But Hawking saw it differently. To him, the singularity was not a wall. It was a window, a place where our understanding had to grow. In those years he often described black holes, not as tombs, but as laboratories. And the early universe, not as a mystery, but as a beginning waiting to be unfolded. The theorems were not only important for what they proved, but for what they allowed next. They gave physicists permission to stop treating singularities as errors, to begin taking them seriously, to study them with the same rigor once reserved for galaxies and stars. They said, if you want to understand space, understand where it fails. If you want to understand time, trace it to the point where it breaks. And that is what Hawking did for the rest of his life. He never stopped asking what lies beyond, and he never accepted the idea that the answers were out of reach. In the theorems, he saw more than logic. He saw philosophy. He saw the boundary between knowledge and wonder, the moment when the human mind, pushed to its limit, must invent new tools or be left behind. He also saw symmetry. Black holes and the Big Bang were not opposites. They were reflections, each a singularity, each a place where the known becomes unknowable, and if they mirrored each other, perhaps the key to one could unlock the other. This insight would fuel his later work on entropy, on information, on the possibility that black holes might evaporate, but none of that would have been possible without the theorems. They were the bedrock, the unyielding stone beneath the shifting soil of speculation. Penrose had carved the shape, Hawking had placed it in the sky. Together, they changed what we expect of the universe. Not perfection, not simplicity, but necessity. They taught us that singularities are not rare, they are part of the story, and if we want to tell that story completely, we must go where the light can't reach. We must follow the lines of curvature all the way in. Old, white, to the end, where time stops, where space folds, where understanding must begin again. And that is the gift of the Hawking-Penrose Theorems. Not that they close the book, but that they force us to write a new chapter. Hawking radiation. When black holes glow. Black holes were never supposed to glow. They were meant to be final. A sentence without a period, an object that eats light and returns nothing. Not heat, not sound, not a flicker of energy. They were the ends of stories, massive stars collapsing under their own gravity, crushed into a silence so deep that not even a photon could escape. But Stephen Hawking refused to accept that silence. He believed that even the darkest places in the universe might have something to say, and to hear it, you'd have to listen not with telescopes but with mathematics. And not just Einstein's math, but the trembling, chaotic language of quantum mechanics. This was the problem that sat before him. Einstein's theory of general relativity and the strange world of quantum physics didn't get along. They were like rival kings in a universe with one throne. General relativity explained gravity, orbits, curved space-time, black holes. Quantum theory explained atoms, energy levels, uncertainty, and all the chaos of the subatomic world. Each was powerful. Each worked. Each had been tested. But when applied to the same problem, like the edge of a black hole, they clash. Hawking knew that to truly understand black holes, he had to step into that collision. He had to explore the event horizon, not as an abstract shell, but as a battlefield between the smooth geometry of gravity and the flickering randomness of the quantum vacuum. What he discovered changed physics forever. Let's slow things down. What is the vacuum really? To most of us it means emptiness. No particles, no light, no sound. But in quantum theory, the vacuum is not empty. It's seething, alive with temporary particles that pop into existence for the briefest flickers of time, then disappear. Particle-antiparticle pairs, created out of nothing, annihilating each other back into the void. This happens everywhere, all the time, even in the emptiest space. Now imagine one of those pairs appears right at the edge of a black hole, just close enough that one particle falls in, and the other escapes. The black hole swallows one, but the other lives. To an outside observer, it looks like the black hole has emitted something, a particle, an energy. And this isn't just an illusion, it's real. The escaping particle carries energy away, and energy comes from mass, which means the black hole loses mass. This was Hawking's great insight. Black holes don't last forever. They radiate, they shrink, they fade. Over time, a black hole slowly bleeds away its own mass through a process now called Hawking radiation. It was shocking, not because it broke a rule, but because it joined two rules. that had long refused to cooperate. Quantum field theory, meeting general relativity, on the curved backdrop of a black hole. Before this, physicists thought black holes could only grow. They could consume, but they couldn't give back. They couldn't glow. They were the perfect prisms. Hawking showed that they weren't. They were more like slow-burning coals, faint at first, nearly undetectable, but gradually releasing heat until nothing is left but empty space. The implications were enormous. It meant black holes had a temperature, not just a surface or a boundary, but a thermodynamic identity. They obeyed laws of heat, entropy, and energy flow. That alone was remarkable, but it led to something deeper. If black holes radiate, and that radiation carries energy, what else does it carry? What about information? When something falls into a black hole, we assume it's lost forever. Not just physically, but informationally. Its quantum state, its properties, its arrangement, all gone. But quantum mechanics says that information is never destroyed. It can be scrambled, hidden, but never truly erased. So, what happens when a black hole disappears? Where does the information go? Hawking initially believed that it was lost, that the black hole simply erased it. This created a paradox. If true, it meant that quantum mechanics itself might be incomplete, that the foundational rule of reversibility, the idea that a system's evolution can be retraced, might break down at the event horizon. This was called the black hole information paradox, and it became one of the most debated questions in modern theoretical physics. Over time, Hawking's position shifted. Later in life, he acknowledged that perhaps information was not lost, that it might be preserved in subtle quantum correlations within the radiation itself. Not easily detected, but still there. Other physicists proposed alternatives, that the information might be stored on the event horizon, or that it could emerge through quantum entanglement. Some imagined the horizon as a hologram, a surface that records everything falling in, like a cosmic ledger. Hawking's work sparked all of this, not by answering every question, but by forcing them into the light. It turned black holes from endpoints into laboratories, not just objects that consumed, but objects that revealed, that tested our deepest assumptions about time, energy, and truth. And it brought physics closer to something long sought after, a unified theory, a single framework that could describe gravity and quantum fields under the same set of principles. Hawking radiation was a clue, a signpost at the edge of understanding. It didn't explain everything, but it told us we were missing something big. And it told us where to look, because to describe how a black hole fades, you need both theories: relativity to describe the curve, quantum mechanics to describe the flicker, and at their meeting point, a glow. There's something haunting about the idea. A black hole, once thought to be eternal, slowly erodes. Over trillions of years, its mass leaks away. Its horizon shrinks. Its temperature rises. The radiation accelerates. Near the end, the black hole blazes, not with fire, but with pure quantum fury. And then, it vanishes. What's left? Does the radiation retain the memory of everything the black hole consumed? Can we decode it? Rebuild it? Reverse it? Or is there something missing still? That's the mystery. And it began with one question. What if black holes aren't silent? Stephen Hawking didn't stumble on this idea. He earned it. Through calculation, through risk, through the merging of worlds that had never been joined. He followed the math to its breaking point. And instead of turning away, he kept going. In doing so, he transformed black holes from cosmic dead ends into glowing beacons of unfinished knowledge. He gave them temperature, entropy, decay. He made them dynamic. He made them human, struggling, losing, radiating away everything they had gathered. And maybe that's why his work resonates. Because in every black hole that fades, there is a metaphor. For life, for legacy, for the way even the most powerful must return their energy to the universe. Nothing is permanent, not even darkness, not even silence. The universe is a place of exchange. Mass becomes light, structure becomes heat, boundaries are tested, laws are rewritten, and at the center of it all, a man in a chair, with a voice synthesized by a machine, telling us that black holes glow, telling us that endings aren't what we thought they were, telling us quietly that even in the places where light cannot escape, something shines. Entropy and the arrow of time. There is a direction to time. We feel it, even if we can't define it. We wake, we age, we forget. Memories form in one direction. Cracks spread across the surface of things. Stars burn, not backward, but forward. It moves like a current we cannot resist. And no matter how reversible the equations of physics seem, there's something in our reality that insists. This moment came after that one, and the next will follow. Stephen Hawking was obsessed with that current. Time in its purest form doesn't flow in relativity. It exists as a dimension, as a coordinate, stretching across the fabric of space-time just like space does. But we don't live in geometry, we live in stories, and stories need a before and an after. The question is why? Why does time move forward for us, when so many of our physical laws work just as well in reverse? Why does cream mix into coffee but never unmix? Why do we remember yesterday but not tomorrow? Why does the universe seem to age? The answer, at least in part, is entropy. Entropy is not disorder. Not exactly. It's possibility. It's the number of ways a system can arrange itself. A deck of cards in perfect order has low entropy. Shuffle it. Entropy rises. The more ways to rearrange something without changing its observable state, the higher the entropy. Entropy explains why heat spreads, why smoke rises, why your breath fogs a mirror that never refocuses into your lungs. And it's not just a pattern, it's a law. The second law of thermodynamics. In an isolated system, entropy always increases. That law is what gives time its direction. Without it, we'd have no arrow. Events could just as easily run backward as forward, but in this universe, entropy increases, and with it, so does the illusion of time flowing. Hawking understood this deeply, and for him, entropy wasn't just about heat engines or chemistry, it was about black holes, and about the entire universe itself. In classical general relativity, black holes had no entropy. They were defined by just a few quantities: mass, charge, spin. The so-called no-hair theorem said that black holes forget almost everything about the matter that created them. They are smooth, simple, bald. But that posed a problem. If something with structure falls into a black hole, and all that remains is mass, spin and charge, then information is lost. Structure is lost. Entropy seems to decrease, and that violates the second law. Unless black holes have entropy of their own. Unless that surface, the event horizon, stores some kind of hidden complexity. In the 1970s, physicist Jacob Bekenstein proposed that black holes do have entropy, and that it's proportional to the area of their event horizon. Not the volume, but the surface. It was a strange idea, but Hawking took it seriously. He calculated it, combining thermodynamics, quantum theory, and gravity. What he found was astonishing. He discovered that black holes radiate, yes, as we now call Hawking radiation. But more than that, they have a temperature, a very cold one, but real. And with temperature comes entropy. He derived a formula. The entropy of a black hole is proportional to the area of its event horizon divided by Planck units. It was the first time someone had united so many parts of physics in one expression. Suddenly, black holes weren't exceptions to thermodynamics. They were part of it. They were thermodynamic systems, obeying the same rules as everything else. It meant the second law still held. If something falls into a black hole, the entropy doesn't vanish. It's added to the entropy of the black hole itself. And as the black hole evaporates, the radiation it emits carries that entropy away. This brought entropy into the heart of cosmology, not just as an afterthought, but as a guiding principle. Hawking began to ask larger questions. What was the entropy of the entire universe? How did it start so low, and why does it continue to rise? The early universe was hot, dense, and smooth. Surprisingly smooth. That's strange, because a smooth universe has low entropy. There are fewer ways to arrange smoothness than lumpiness. So if entropy tends to increase, why did the universe begin in such an unlikely state? No one knows the full answer. But it matters, because it sets the arrow of time. If the universe had started in a high entropy state, it might have gone nowhere. No evolution, no complexity, no stars forming, no life. Instead, Something about that initial singularity created order, low entropy, and from that order, everything unfolded. As entropy increased, the universe expanded. Structures formed. Heat moved. Events began to distinguish themselves. Hawking suggested that perhaps entropy isn't something imposed, but something that emerges as the universe cools. Perhaps near the singularity, time itself behaves differently. Perhaps the idea of direction only becomes meaningful as space expands and entropy begins to rise. This tied directly into his no-boundary proposal, the idea that time may have started like a curve, gradually becoming real, not all at once. In that view, entropy doesn't explode into being. It emerges, gently, alongside time. He also explored the idea that black holes are the most entropic objects in the universe, that the entropy they contain is not a curiosity, but a clue. Maybe the end state of everything is a kind of information smoothing, a spreading out of all that was once tightly wound. The arrow of time is not just about aging. It's about memory, about what we can know and how we can know it. We remember the past because it was lower in entropy, fewer configurations, easier to encode. The future, with its rising entropy, is harder to predict. This is why broken glass doesn't reassemble, why dead stars don't ignite again, why you can't untoast bread. It's not just engineering, it's entropy. And Hawking's genius was in recognizing that this principle, this simple tendency of systems to spread, is the skeleton of time. We often imagine time as a river, but it's not the water that flows, it's the imbalance. The movement from likely to more likely, from structured to unstructured, from simple to complex, and eventually back to simple. Entropy isn't chaos, it's direction. It's why the cosmos began in fire and ends in darkness. There's something poetic in that. We rise into patterns only because there is energy to borrow. Structure only lives in the tension between what was and what will be. Eventually, the energy spreads. The difference fades. Heat becomes uniform. Light is redshifted beyond sight. And time, as we understand it, ceases to mean anything. Hawking called this the heat death of the universe. Not an explosion, not a collapse, but a dimming, a final equilibrium where entropy is maximized and no work can be done. It's not apocalyptic, it's serene, the last sigh of a cosmos that used its time well. Until then, the arrow moves forward. Entropy climbs, and we live in the middle between a smooth beginning and a scattered end. And in that middle, we can ask questions, we can look backward and forward, we can wonder what made the arrow tick. Hawking never claimed to have all the answers, but he reshaped the questions. He brought thermodynamics to the center of cosmology. He made entropy into a storyteller, not a destroyer, but a guide. Because without entropy, time is directionless, and without time, there is no growth, no life, no wonder, no voice on a machine telling us that black holes fade, and that the universe began not with disorder, but with a miracle of improbable structure. That miracle was fleeting, but it was enough. The information paradox. What gets lost in the void? Imagine writing something down and watching the paper burn. The words vanish, the ink curls, the ash scatters. But if you believe in physics, you know the story isn't over. The atoms are still there. The molecules have changed form. The energy released is measurable. Nothing is truly lost, just rearranged. That's the promise of quantum mechanics, a promise that the universe remembers. But black holes challenge that promise. They offer a place where matter disappears beyond reach, where information seems to cross a one-way boundary, never to return. And that contradiction became the greatest unresolved question Stephen Hawking ever posed. The paradox begins at the event horizon, that invisible surface, where escape becomes impossible. Cross it, and no path leads back. Not for matter, not for light, not for information. The black hole continues to grow. It swallows whatever comes near. Gas, dust, light, memory. And in return, it offers nothing. A dark, featureless sphere, defined only by its mass, spin and charge. This was the standard view, and under general relativity it worked. But then Hawking introduced quantum mechanics to the edge, and suddenly, black holes began to glow, not with visible light, but with Hawking radiation, a quantum phenomenon where particles escape the vacuum just beyond the event horizon, taking a sliver of energy with them. The black hole, once thought eternal, now began to shrink. Slowly, patiently, it evaporated. At first, this seemed elegant, a bridge between theories, a reconciliation of gravity and quantum fields. But the cost was steep. If black holes evaporate, what happens to the information they consumed? Suppose you throw a book into a black hole, not just any book, a book full of memories, formulas, patterns, a book with structure. As the black hole radiates, it releases particles, but those particles are random, thermal, featureless. When the black hole is gone, all that remains is heat. The particles carry energy, but not meaning. No imprint of the book. No trace of what fell in. In quantum mechanics, this is forbidden. The evolution of a system must be unitary, which means reversible in principle. Every change is just a rearrangement. Nothing is erased. But Hawking's calculations suggested otherwise. The radiation had no structure, no memory, no pathway back to the original state. This was the black hole information paradox. At its heart, it was a battle between two beliefs. Quantum mechanics said information could not be destroyed. General relativity said black holes erased it. They couldn't both be right. And so, the paradox stood. At first, many sided with Hawking. The math was clean. The logic, compelling. Black holes were entropy machines. They radiated away their mass, leaving nothing behind. But others were uneasy. The destruction of information would shatter not just quantum mechanics, but the foundation of physics itself. Over time, more voices entered the debate. Some argued that the information was not truly lost, just hidden, scrambled, encoded in ways we didn't yet understand. The radiation, they claimed, wasn't purely thermal. It held subtle correlations. Not enough to reconstruct the original book, but enough to preserve its possibility. Others suggested the event horizon was not as final as it seemed. That information might be stored there, not inside the black hole, but on its surface. This was the beginning of holographic theory, the idea that the universe itself might store its deepest truths on lower dimensional boundaries. According to this view, a black hole's horizon isn't just a border, it's a screen, a record of everything that has crossed it, not in the particles themselves, but in the pattern, the arrangement, the entropy. The theory gained traction. Physicists like Gerard Hooft and Leonard Susskind developed models suggesting that all the information inside a volume of space could be encoded on its surface area. This holographic principle found support in string theory, in Abad-CFT duality, and in the growing belief that our universe might itself be a projection from a more fundamental boundary. For Hawking, this was unsettling. It meant his original conclusion might be wrong. That information was not lost, but transformed, not destroyed, but disguised. And slowly, over the decades, he changed his mind. In 2004, in a public presentation, Hawking announced a reversal. He proposed that information does escape, that subtle interactions between the black hole and its surroundings allow quantum data to seep out during the evaporation process. He offered a new model, one that preserved unitarity and held on to the integrity of quantum mechanics. But the details remained elusive. How, exactly, was the information encoded? Could it be recovered? Or was it so scattered as to be practically irretrievable? And if black holes preserve information, what becomes of their singularities? Are they real, or replaced by some deeper structure? The paradox still lives, because it's more than a calculation. It's a confrontation with the limits of what we can know. A black hole is a riddle, with the answer hidden inside itself. To solve it, you need a theory that works at every scale, that describes both the geometry of space and the vibrations of quantum fields. And that theory still waits to be born. Some physicists suggest that space-time itself may be burgeoned, not fundamental, but a result of information flow, that the geometry we see is just the shadow of a deeper computation we don't yet understand. Others propose firewalls, violent boundaries at the event horizon that destroy anything falling in, breaking relativity, but preserving information. But each solution creates new problems, and so the paradox continues. pulling physics into deeper questions. What is space? What is time? What is a particle? What is real? The black hole information paradox is not just about physics, it's about meaning. It asks whether the universe forgets, whether history matters, whether memory, in all its forms, can truly disappear. It touches on philosophy, on identity, on the structure of causality itself. Hawking didn't pretend to have every answer, but he gave the question form. He showed how even the cleanest theories can stumble on the edge of collapse. He turned black holes into crucibles of theory, places where logic is melted down and reshaped. In doing so, he changed how physicists think. He reminded them that a paradox is not a failure, it's a torch, a guidepost, a flare thrown high above the dark surface of our ignorance, and though the paradox remains, it has already borne fruit. It has forced collaboration between gravity and quantum theory. It has inspired new models, new geometries, new ways of thinking. It has made physicists humble and bold, because if the universe does preserve information, then every moment is eternal. Every interaction leaves a trace. Every structure carries a ghost of what made it. That's not romanticism. That's physics. It means the heat from a black hole might still whisper what it once devoured, not in words but in correlations. In the quiet murmur of quantum entanglement. It means the universe, even in its darkest places, remembers. And it means Hawking's great paradox isn't just about what gets lost, but about what endures. Not every riddle has a solution, but some are worth living with because in chasing them we become more precise, more careful, more alive to the mystery. And so we return to the edge of the event horizon, not to watch things fall in, but to ask what they leave behind. A ripple, a mark, a question that glows faintly against the void. Quantum gravity, where Einstein meets the small physics, has two great languages. One speaks in curves and continuity, the smooth, flowing elegance of general relativity. The other stutters in probabilities, in uncertainty, and jittering particles, the sharp, granular dialect of quantum mechanics. Each works on its own. Each describes a universe that is consistent, predictable, extraordinarily accurate. But they do not agree. General relativity explains the large stars, planets, galaxies, gravity itself. Quantum mechanics explains the small atoms, electrons, forces, and fields. The problem comes when the large becomes small, when immense mass collapses to a point, when curvature grows infinite, when time stops being a coordinate and becomes a riddle. This is where quantum gravity begins, not as a theory, but as a necessity, a question that neither of our languages can answer alone, and no one understood that better than Stephen Hawking. He saw the failure lines clearly, black holes and singularities, places where both theories were required, but neither was sufficient. General relativity broke under extreme density. Quantum theory ignored gravity almost entirely. The two great pillars of physics stood like ancient monuments on opposite sides of a chasm. Brilliant, incomplete, incompatible. The task was to build a bridge between them, and Hawking, for much of his life, tried to lay the stones. Quantum gravity is not a single theory. It is a goal, a vision of unification, a dream of a physics that speaks one dialect from the smallest particle to the widest arc of the cosmos. It is the attempt to describe gravity not as a curve, but as a quantum field, to quantize space-time itself, to treat the structure of the universe not as smooth and continuous, but as grainy, discrete, pixelated at the smallest scales. Imagine zooming in on space until the very fabric becomes visible. Not empty distance, but something textured, vibrating, shifting, alive with uncertainty. This is the domain of quantum gravity, and it is still unmapped. There are many paths toward it. Some physicists explore string theory, which imagines that particles are not points, but tiny loops of vibrating energy. Different vibrations create different particles. In this view, gravity emerges as a vibration of a string, not as curvature but as resonance. Others pursue loop quantum gravity, which attempts to quantize space directly. It suggests that space is made of loops, interwoven into a spin network. At the smallest scales, space becomes digital, discrete, countable. These theories differ wildly. String theory imagines extra dimensions, possibly up to 11. Loop quantum gravity stays in 4, but changes the shape of space itself, yet both agree, space is not smooth. Time is not continuous, the universe at its roots is granular. Hawking didn't pick a side, he was interested in the implications, in what these models could say about black holes, about entropy, about the beginning of everything. He used the tools of both camps. He explored imaginary time. He modeled wave functions of the universe. He treated gravity like a quantum system, even when the theory was incomplete. His most famous attempt to merge the two worlds came in the form of the no-boundary proposal. Alongside James Hartle, he suggested that the universe didn't begin with a singularity in time, but rather as a smooth surface with no boundary. Like the South Pole, where direction loses meaning, the beginning of time could be a rounded point, where time becomes space. To model this, Hawking used a quantum approach. He imagined a wave function for the universe, not a single history, but a sum over all possible histories, not a start, but a blur, an emergence. This was not philosophy, it was an equation, and in that equation Hawking tried to capture the seed of all that followed, without invoking a creator or a cause. It was quantum gravity in practice, not a full theory, but a glimpse, and it offered a way to talk about the origin of time without hitting a wall, a way to soften the singularity into something comprehensible. But the work was far from complete. The deeper physicist looked, the stranger things became. At the Planck scale, the smallest possible scale, where gravity and quantum effects are equally strong, space and time lose their meaning. Distances fluctuate, energy spikes randomly, geometry becomes probabilistic, even causality, the order of events becomes uncertain. This is the realm of quantum foam, a concept proposed by John Wheeler, but deeply relevant to Hawking's work. In this view, the vacuum is not empty. It is a storm of tiny fluctuations, bubbles of space-time forming and collapsing, virtual black holes flashing in and out of being. Reality becomes turbulent, and nothing can be trusted to stay where it is, or to remain what it was. To make predictions in this realm, you need a theory of everything, a single framework that unifies all forces, all particles, all geometries. And we don't have it yet, but we have signs. Hawking's own calculations showed that gravity affects quantum fields, that black holes radiate, that information might not be lost, but hidden. And that space, even empty space, has structure. He suggested that even the horizon of a black hole might encode information, that perhaps the entire universe could be described by a theory on its boundary. The seeds of holography were there, the seeds of unification, and all of this pointed to one truth: gravity must be quantized. You cannot describe the early universe without quantum gravity. You cannot understand black holes without quantum gravity. It is the missing piece in the puzzle Hawking spent his life assembling. And yet, the full theory remains elusive, not because the math is wrong, but because we don't yet know what questions to ask. Are space and time fundamental, or are they emergent? Is gravity a force, or a consequence of entropy? Are particles real, or are they just patterns in deeper fields? Hawking believed that answers would come, not through divine revelation, but through persistence, through careful reasoning, through bold mathematics, and through paradox, because paradox, to him, was not failure. It was signal, an arrow, pointing toward what must be discovered next. Quantum gravity is the theory that waits beyond that arrow. It is not finished, it is not agreed upon, but it is coming, and it will be strange. Stranger than strings, stranger than loops, stranger than space without time, or time without meaning, because the universe at its root is not simple. It is layered, textured, laced with uncertainty, bound by rules we do not yet know, but we know they are there, because black holes radiate, because singularities arise, because the cosmos has a shape, and a history, and an origin that defies the language we currently use. And that is why Hawking's work matters. Not because it gave us every answer, but because it showed us where to look, in the overlap, in the tension, in the impossible places where Einstein meets the small, imaginary time and the shape of the universe. We speak of time as a river. We imagine it flowing, always forward, from past to future, carving its path through memory and matter. It seems simple, obvious even, until we try to describe it with mathematics. Then time begins to misbehave. In Newton's world, time was absolute, a ticking clock, steady and indifferent. Every event, every motion, happening against the backdrop of an eternal metronome. But Einstein shattered that idea. He showed us that time bends, that it stretches in gravity, that it ticks more slowly near mass, that it's not a separate backdrop but part of the geometry of space itself. And still, even in Einstein's equations, time retained a direction, a past, a future, a singular thread. But in the equations of quantum mechanics, time is curiously absent. Particles don't evolve in a neat sequence. They exist in superpositions, overlapping states where events are not ordered, but entangled. Probabilities not paths, possibilities not outcomes. To reconcile these pictures, Stephen Hawking took an extraordinary step. He imagined that time, like space, might be curved. Not just in geometry, but in its very nature. He proposed that in certain regimes, especially near the origin of the universe, time could become imaginary. Not in the fictional sense, but in the mathematical one. In complex numbers, the imaginary unit is represented by the square root of -1. It allows us to describe rotation, waves, oscillation. It allows time to behave, not as a straight line, but as a circle. Hawking's bold idea was that near the beginning of the universe, time may not have behaved like time at all. It may have behaved like a dimension of space. Imagine a globe. You can walk north until you reach the pole. After that, the concept of north dissolves. There's no edge, no cliff, just a smooth roundness, where direction becomes meaningless. Now imagine the same is true for time. At the Big Bang, there is no sharp beginning, no singular moment of creation. Instead, time curves. It transitions smoothly from something like space into what we now experience as time. This is the heart of Hawking's no-boundary proposal. The universe didn't begin with a bang, but with a curve, a finite, closed surface with no edge and no boundary. Not in space, not in time. And that curvature, that softness at the beginning, could be described using imaginary time. It's a difficult concept, not because it's abstract, but because it defies our experience. We do not live in imaginary time. We do not feel its rhythms. We exist in real time. Seconds ticking, memories forming, entropy rising. But if Hawking was right, real time is something that emerged from a deeper structure, something smoother, more symmetric. In this early phase, before time as we know it crystallized, there was no causality, no sequence, only a wave function of the universe, a probability cloud, describing all possible configurations of space and time. Hawking and James Hartle developed this into a formal model, a path integral over all possible compact Euclidean geometries. In this picture, the universe has no edge, no singularity, no beginning in the traditional sense. It simply is. Its shape determines its history, its curvature defines its evolution, and time, the time we feel, emerges as part of the solution. This is not poetry, it's physics, but it borders on the poetic, because it changes how we understand existence. If imaginary time is real, if it played a role in the early universe, then the laws that gave rise to everything may not have required a spark. No initial explosion, no cosmic ignition, only a structure that allows itself to unfold. This removes the need for a boundary, and with it, the need for something beyond that boundary. No edge means no cause, no beginning means no external intervention. The universe becomes self-contained, complete, a system with its own rules. Hawking often emphasized this, that the no-boundary model was not just an equation, but a shift in perspective. He once said, "What place then for a creator?" The question wasn't meant to provoke, it was meant to clarify. If the universe is finite but unbounded, then the need for something beyond it fades away. It becomes like the surface of the earth, whole, self-sustaining, without requiring anything outside to define it. This doesn't deny wonder, it deepens it. It means the laws that govern everything may have arisen from the shape of space-time itself, from the symmetry of curvature, from the strange, folded dimensions described by imaginary time. This also ties into entropy. If the early universe was finite and curved, its entropy could have been extremely low, because the number of possible configurations was also limited. As the universe unfolded, space expanded, and entropy began to climb. The arrow of time, the direction we feel so deeply, was born from that growth, from that unfolding. Imaginary time allowed Hawking to model this without hitting a singularity, without needing to break the laws of physics just to start the clock. It gave him a framework for describing the early universe as smooth, calculable, predictable, not chaotic, but structured, not explosive, but elegant. There's also a visual beauty to it. Imagine a sphere emerging from a flat plane. At first it's just a point, then it bulges outward, growing, expanding, and then it moves forward, turning into something linear, something directional. That point of transition from imaginary time to real time is where everything we know begins. And because there is no edge, no cliff, no singular start, there is also no paradox, no before, no breakdown, only geometry. Hawking's model doesn't replace the Big Bang, it reframes it. Instead of a flash, it becomes a bloom. Instead of an explosion, an emergence. It also has consequences for how we think about the universe's fate. If time can be curved at the beginning, can it curve again at the end? If the universe is finite, will it loop? Will time itself soften, fade, bend back inward? Or will the expansion continue forever, leaving only cold, empty space? These are open questions, but imaginary time offers a new way to ask them. It gives us tools to think beyond limits, not by erasing the hard parts of physics, but by expanding the canvas, by allowing time to be complex, to rotate, to loop, to hide its true nature until we're ready to see it. Hawking's use of imaginary time wasn't a trick, it was a revelation. It showed that time might be more flexible than we assume, that what we experience as linear may be a projection, a narrowed slice of a deeper reality, one where beginnings are smooth, not sharp, where history is encoded in shape, not sequence, where the universe does not begin in violence, but in symmetry. This has implications far beyond physics. It changes how we think about causality, about creation, about existence itself. It suggests that what we call the present is not a privileged point, but a consequence, an unfolding from a structure that was always there. It also changes how we think about measurement. In quantum mechanics, observation plays a strange role. It collects probabilities. It defines outcomes. But if time is imaginary near the origin, then there may have been no observers, no measurements, no decoherence, just potential. And out of that potential, a universe. And now here we are, asking questions about time using minds made from its residue, using language built to move in one direction, to describe something that may have started without any direction at all. This is the paradox of our perspective. We are creatures of entropy, of memory, of ordered moments, but the laws we seek to understand may not care about order in the way we do. Imaginary time helps us bridge that gap. It lets us ask what time was before it was time. It gives us a tool to model the birth of the universe, without violating the principles we've built everything else upon. It connects geometry to existence, curvature to causality. And in that connection, we find a kind of freedom, a way to think about the cosmos, without needing a beginning, without needing a before, only a shape that unfolds into stars, into particles, into galaxies, into us. Hawking never claimed that imaginary time was the answer, only that it might be a better question, one that softens the edges, one that removes the need for boundaries, one that lets the universe be self-contained, complete, beautiful. And in that quiet shift from time to structure, from singularity to smoothness, he gave us a new way to imagine where it all began. The no-boundary proposal. There is comfort in edges, a line between one thing and the next, a horizon, a beginning. We build our lives on such boundaries. We mark time with firsts and lasts. We imagine creation as a flicker, a single point where it all began. But what if the universe has no edge? No start, no seam between nothing and something, no corner from which everything unfolded? What if the origin wasn't a place, or a moment, but a curve. Stephen Hawking's no-boundary proposal was not just a model, it was a reimagining of what it means to begin, not with a bang, but with geometry. Not with a singularity, but with smoothness. To understand this idea, we must abandon how we normally think about time. We must step out of our linear intuition and into a realm where time is not a straight arrow, but a rounded path. A contour that folds back on itself like the surface of a sphere. Hawking, with physicist James Hartle, proposed that the early universe did not emerge from a singularity, a sharp, violent point, but from a closed, finite, smooth surface. A beginning that has no boundary. Just as the Earth's surface has no edge, so too could the universe begin with no edge in time. They called it a wave function of the universe, the sum over histories, every possible path the universe could take, integrated together, weighted by probability. These paths included every shape, every geometry, every curvature that smoothly connects a boundaryless origin to what we now observe. And the most probable histories, those that dominate the wave function, are those with no boundary at all. In other words, the universe didn't require a singular moment of creation. It simply exists, emerging from a smooth geometry that transitions naturally from imaginary time to real time. This was radical, because it removed the need for it removed the mystery of initial conditions, and it reframed the Big Bang, not as a rupture in physics, but as a feature of space-time's shape. In Hawking's picture, the laws of physics never broke down. They simply changed form. Time began as a dimension of space, curved, symmetrical, with no preferred direction. And as the universe cooled, as entropy rose, real time emerged. With it came causality, memory, and the arrow of time. This smooth beginning is deeply visual. Imagine a two-dimensional surface, a hemisphere. The bottom is round. There's no edge, no spike. It simply curves, and from that curve, a timeline rises. There is no before, there is only the shape, the surface that gives rise to history without requiring an origin outside itself. It also resolves a crucial issue. In classical cosmology, the singularity is a wall. The equations break. You cannot calculate beyond it. Time starts from an undefined point where the rules of physics no longer apply. But Hawking's no-boundary proposal allows for a fully calculable universe, a model with no place where physics fails, no point at which we must insert divine intervention or step beyond the scientific method. This doesn't mean the universe is eternal, it means it is finite, but unbounded. Like the surface of a sphere, you can walk in any direction forever, but you will never fall off the edge. That idea that the universe needs no outside, no external cause, became the foundation of Hawking's cosmology, and it had profound consequences. If the universe has no boundary, then asking what happened before the Big Bang becomes meaningless. There is no before, there is only a region where the concept of time itself blends into space. This removes the need for a prime mover. It eliminates the mystery of why the universe chose to begin at one moment rather than another. Instead, beginning becomes a kind of illusion, a feature of our perspective. The same way we think of sunrise as the sun moving across the sky, when in truth, it's us who move. Hawking's model doesn't erase creation, it reframes it. It shows us a cosmos that is not born out of nothing, but out of structure, out of the very laws it obeys. But how do we test this? The no-boundary proposal is elegant, but elegance is not evidence. Hawking believed that predictions could still emerge. The model makes assumptions about initial conditions. It implies certain distributions of cosmic fluctuations, certain patterns in the microwave background radiation, the ripples left over from the early universe. If the theory is correct, these ripples should show statistical signatures, subtle features that differ from those predicted by other models. And so, cosmologists continue to measure, to observe, to scan the skies for the fingerprint of a universe that had no beginning in the traditional sense. The evidence so far is not conclusive, but neither is it contradictory. Hawking's model remains one of the leading contenders for the true shape of the origin. It also offers insight into why the universe is so homogeneous, why matter is spread evenly across vast distances, why temperature differences are measured in microkelvin. A no-boundary start explains this as a natural result of the geometry of creation. Smooth inputs yield smooth outcomes. And yet, quantum fluctuations, Small inevitable variations grew into galaxies, stars, life. So from a boundaryless beginning, complexity arises. Structure from symmetry, diversity from uniformity. This is not just mathematically satisfying, it's narratively powerful. Because it means that the laws of physics don't just allow for us, they lead to us. Not by intention, not by design, but by consequence. Hawking's no-boundary model doesn't make humans inevitable, but it makes us possible in a universe that explains itself from the inside out. And this, perhaps, is the heart of it. A boundary implies a beyond, something else, something not described by the system itself. To remove the boundary is to say, this is enough. This structure, this curvature, this self-contained set of laws, the universe needs nothing outside itself to unfold. Some found this unsettling. They wanted a first cause, a moment of creation, a hand at the switch. But for Hawking, removing that necessity was a triumph of science. It showed that cosmology could be complete. That's not the same as saying we know everything, but it means we know where to look, that we can keep asking, and refining, and observing, without ever needing to step beyond the frame. And perhaps most importantly, it means the universe is comprehensible, not easy, not simple, but describable, a place where the rules hold even at the edges, because there are no edges. This aligns beautifully with quantum mechanics. In the quantum world, probability rules. You do not get a single outcome. You get a wave function, a landscape of possibilities. The no-boundary model treats the entire universe as a wave function, every possible geometry, every possible configuration, integrated into one mathematical object, and from that, our universe emerges as one history among many, a path through possibility. It's not that the universe was chosen, it's that this is where the math led. This path, this curvature, this evolution, not by accident, not by fate, but by structure. And so the idea of nothing loses its power. There is no empty void from which the universe burst forth. There is no external stage on which the curtain rose. There is only geometry, only the wave function, only the no-boundary. And from that, all things follow. Stephen Hawking didn't claim this was final. He knew the theory would evolve, that better models would come, but he offered us a lens, a way to see the beginning without looking outside the frame, a way to describe creation as part of the system itself, beginning that isn't a beginning, a surface with no edge, a curvature so perfect it needs no cause, just existence, unfolding, naturally, the birth of the universe without a bang. The universe did not begin with fire. It did not erupt into existence with a deafening roar. It did not explode from a point into space, because there was no space to explode into. No outside, no before, only curvature, quiet and complete. We call it the Big Bang. But Stephen Hawking suggested something else, something quieter, something smoother, a beginning not marked by violence, but by transition. What we call the Big Bang was not a bang at all. Not in the way explosions work, not in the way sound travels through air, not in the way forces collide. It was a boundaryless origin, a moment when time crystallized out of geometry, when space became real, and when the universe emerged from symmetry into history. This was the natural consequence of Hawking's no-boundary proposal, a universe that starts not at a point, but across a smooth surface finite in size, but with no edge. The birth of our cosmos, then, was not a singularity, it was a curve. And from that curve, everything unfolded. But to understand this birth, we have to abandon the picture we grew up with, the idea of a fireball bursting into void. That's an image born of metaphor, not mathematics. There was no fireball, there was no flash, there was only density, temperature, and an expansion of space-time itself. And this expansion didn't happen inside space, it created space. Every point moved away from every other point, not because something pushed them, but because the fabric between them stretched. The Big Bang was not the start of motion, but the start of distance, the start of difference, the beginning of structure. And yet, what came before? Hawking's answer was simple and profound. The question itself dissolves. Before the Big Bang, there was no time. Not because the clock stopped, but because the clock had not yet formed. In the model he built with James Hartle, the early universe was described using imaginary time, time as geometry, time as another axis of space. And as the universe expanded, imaginary time rotated into the real time we experience. This was not speculation. It was a shift in coordinates, a mathematical reorientation that removed the singularity and replaced it with smoothness. There is a beginning that requires no break in physics, a model where the laws hold at every point, including the point where history begins. This concept rewrites our sense of origins. It says that the universe did not explode into being, but emerged. Softly, naturally, inevitably. And with that emergence came space, and time, and energy. From this geometry, the universe didn't ignite. It unfolded. Imagine a field of potential, quiet and flat, no direction, no time. Then a gentle ripple, a fluctuation. One configuration among many possible histories becomes real. This is not an accident. It is the nature of quantum beginnings. A wave function settles. A state becomes dominant. And the universe begins its expansion. This doesn't deny heat, or density, or the immense pressure of the early cosmos. Those still exist, but they are not born from a singular point. They are part of the unfolding. They are consequences of curvature, not eruptions from nothing. Hawking's work reframed the moment we've long called the Big Bang. He kept the physics, the rapid expansion, the background radiation, the structure formation, but he removed the paradox. He smoothed the edge. He replaced the bang with a bloom. And in doing so, he gave cosmology a beginning that doesn't need to break down, a beginning that follows the rules. This also changed how we think about the universe's potential size. In a no-boundary model, the universe can be finite, but without edges. Like a sphere, it can curve back on itself. It may be large, it may even appear infinite from our limited perspective. But it began with symmetry. And from that symmetry, entropy grew. Time gained direction, complexity emerged. This also influences how we think about inflation. In modern cosmology, the early universe is believed to have undergone a period of rapid, exponential expansion. This explains the uniformity we see, the flatness, the lack of magnetic monopoles. But the conditions required for inflation are very specific. Hawking's model, with no boundary, naturally leads to inflation. The geometries that dominate the wave function are those that expand rapidly. In this sense, inflation is not something added, it is something expected. And once inflation begins, space grows. Quantum fluctuations are stretched. They become seeds for galaxies, for clusters, for everything we see. So from a boundaryless origin, we get structure. From silence, pattern. From geometry, motion. But what about the question of cause? In our daily experience, every event has a cause. Push a ball, and it rolls. Strike a match, and it burns. But Hawking's model removes the cause of the universe itself, because cause requires time, and before time there is no cause, only state, only geometry. In this way, the no-boundary universe is not caused. It is. It simply exists, as the most probable history emerging from the sum of all possible histories. This doesn't mean we are an accident. It means we are a realization of a lawful system that includes its own beginning. This idea makes some uncomfortable. They want a trigger, a hand at the switch, a fire at the fuse. But in Hawking's view, a self-contained universe is not less majestic. It is more so. It obeys its laws even at the moment of origin. It includes its own beginning without needing anything else. And that is powerfully liberating, because it means we can study the universe without assumptions, without divine gaps, without unknown forces outside the system. It means cosmology can be complete, not perfect, not finished, but self-consistent. This also invites new questions. If the universe began without a bang, can it end without a whimper? If beginnings are smooth, can endings be soft too? Is the universe cyclic? Will it curve back into imaginary time? Will time itself dissolve into space once more? These are open questions, and Hawking never claimed to know. But he gave us a framework to ask them from within the laws, within the math, within the boundaryless system he helped define. This changes how we think about the total energy of the universe. Some physicists suggest that the total energy may be zero. Positive energy in matter and motion balanced by negative energy in gravity. a perfect accounting in a closed system. In a boundaryless universe, this becomes plausible. The net energy could be nothing, and from nothing, everything. But again, this is not nothing in the philosophical sense. It is not emptiness. It is a structured, calculable state, a mathematical whole, a foundation not of absence, but of possibility. So what does it mean to say the universe was born without a bang? It means the transition from non-time to time was smooth. The shift from potential to presence was continuous. It means the early universe was not a firework, but a wave. A wave function, a swelling surface that gave rise to dimension, to causality, to expansion. It means the most violent moment in cosmic history may have been quiet, structured, symmetrical. It means that before motion there was curvature, before history there was shape, and from that shape came everything. A brief history of time, ideas that changed the world. The universe is ancient. Its story is told in light stretched thin across space, in fossil radiation, in the quiet gravity of distant galaxies. Its language is math, its tone indifferent, and yet, somehow, it speaks to us, not in syllables, but in awe. Few people have ever translated that language into something the world could understand. Fewer still have done it, without losing the wonder along the way. Stephen Hawking did. When he published A Brief History of Time in 1988, he did not just release a book, he cracked open the cosmos for readers who had never studied physics, never solved an equation, never imagined the structure of time. The book was a phenomenon. It sold more than 25 million copies. It was translated into dozens of languages. It became a reference, a gateway, a household name. But what made it resonate was not the math. There was almost none. It was the clarity, the refusal to simplify the ideas, but a commitment to making them accessible through metaphor, through story, through structure. This was not a book that talked down. It talked through. It walked with the reader. It assumed curiosity, not knowledge. And what it gave in return was a glimpse of everything, of how time began, of how black holes bend light, of how quantum mechanics and relativity pull the universe in different directions. Hawking took all the questions he had spent a lifetime pursuing and gave them to the world. The book begins with deep time, with the understanding that our cosmos has a history, that it changes, that stars are not eternal, that the night sky is a story still being written. This idea, though common now, was revolutionary for much of history. For centuries, people believed that the heavens were fixed, unchanging, perfect. Hawking showed that they are anything but. Stars are born, they age, they collapse. Galaxies collide. Space expands, time stretches, and in that unfolding, we find our place. Small, yes, but not meaningless. Breathe. He explained the Big Bang as the beginning of time, not an explosion in space, but the creation of space itself. He described the smoothness of the early universe and the fluctuations that seeded structure. He showed readers that cosmology is not about stargazing. It's about understanding reality at its deepest levels. He moved through relativity, the way gravity bends space, the way mass curves time, the way clocks tick differently, depending on how fast or how far they fall. He explained how black holes are not holes at all, but dense regions from which light cannot escape. He introduced the concept of an event horizon, a point of no return, not because of a wall, but because of a limit in the paths that light can take. And then he turned to quantum theory. He explained uncertainty, the idea that you cannot know both position and momentum with absolute precision, that particles do not follow single paths, but all paths, weighted by probability. He used this to describe how black holes radiate, how nothing is ever truly still, how even in the vacuum, particles flicker into being. He called this Hawking radiation, and he introduced it in a way that non-physicists could grasp, not through equations, but through insight, through analogy, through language. This was the true power of A Brief History of Time. It was not just a book about science. It was a book about understanding. Hawking didn't avoid the big questions. He asked, why is there something rather than nothing? Why does the universe exist at all? What is the fate of time? Is the universe infinite or finite? Is there a grand unifying theory? He tackled determinism, the idea that the universe unfolds from fixed initial conditions, and he explored whether quantum theory, with its built-in uncertainty, undermines that determinism. He addressed God, not as a theological figure, but as a metaphor for ultimate explanation. He famously asked whether there was room for a creator, if the universe could be fully described by the laws of physics. His tone was not combative. It was curious. He wanted to know whether the universe required anything outside itself, and he leaned toward no, not from arrogance, but from consistency. The final chapter of the book asked, if we discover a complete theory, it should be understandable by everyone. Then we shall all, philosophers, scientists, and just ordinary people, be able to take part in the discussion of why we and the universe exist. This was not a dismissal of mystery, it was an invitation, a belief that wonder does not depend on ignorance, that beauty does not disappear when we understand its structure. That was one of Hawking's most important legacies. He made physics human. He made cosmology personal. He showed that understanding does not kill awe. It deepens it. Breathe. He proved that the story of the universe is not reserved for experts, that anyone willing to think slowly, to be patient, to engage with difficult ideas, can touch the edge of time. That's why the book mattered, not because it simplified science, but because it respected the reader. It gave them the chance to walk beside him, to peer into black holes, to imagine the early universe, to consider the end of time. And that invitation changed lives. People became physicists because of a brief history of time. They became teachers, writers, philosophers, or simply more curious versions of themselves. The book didn't answer every question. It didn't claim to. But it showed that asking was enough, that seeking was worthwhile. That complexity was not a wall but a doorway. It also changed how the public viewed scientists. Hawking became a symbol, not of disability, but of brilliance expressed through limitation. His wheelchair, his voice synthesizer, his slow typing, none of it diminished what he could convey. He was proof that the mind is not bounded by the body, that insight does not require mobility, that intellect is a force all its own. The image of Hawking, tilted slightly, eyes sharp, voice monotone but expressive, became iconic, not because he sought fame, but because he represented something rare, a deep thinker who could also speak to the world, and he did so without arrogance, without theatrics. He simply shared what he knew, and asked us to follow. The success of A Brief History of Time was not an accident. It was a result of clarity, of intention, of a belief that the universe is not too complicated for ordinary people to understand. Yes, it is strange. Yes, it is vast, but it is also structured, graspable, legible. If we are willing to stretch, to slow down, to let go of certainty, we can begin to see the shape of it, and in seeing that shape, we see ourselves because we are not separate from the universe. We are part of it, made of its elements, shaped by its history, participants in its future. When Hawking spoke of time, he wasn't just talking about distant stars. He was talking about the fabric of reality that runs through us all. In that way, A Brief History of Time was not a physics book. It was a human book about where we came from, about what it means to exist in a universe with laws and with limits, about how knowledge itself is an act of participation. Even decades later, the book remains relevant, not because science hasn't moved forward, it has, but because Hawking's approach remains rare, to teach, not just facts, but frameworks, to share, not just results, but questions, to open the door to the cosmos and say, come in. The universe in a nutshell, dimensions, branes, and strings. There's a quiet assumption beneath the way we move through life, that the universe has 3 dimensions of space and 1 of time. Forward, backward, left, right, up, down, and always, the steady drift of time beneath it all. But what if that's only part of the story? What if our experience of space and time is a shadow of something larger, a projection of a deeper geometry we cannot yet see? Stephen Hawking believed the universe might be far stranger than we perceive. In The Universe in a Nutshell, he invited us to think beyond the boundaries of our senses. He asked us to imagine a cosmos, not limited to the familiar, but one shaped by invisible dimensions, hidden symmetries, and delicate strings that vibrate beyond detection. The book followed a brief history of time, but it was not a sequel. It was an expansion, an attempt to explore the frontiers of the known and the speculative. At the heart of this exploration was the idea that our universe may have more than 4 dimensions, that the laws of physics, when pushed to their limits, require more room to breathe. String theory is one of those frameworks. It begins with a simple shift. Instead of treating fundamental particles as point-like dots, it treats them as one-dimensional loops, tiny vibrating strings. Each vibration creates a different particle, a different mass, a different force. But strings need space to move, and not just the 3 dimensions we know. For the equations to work, string theory requires extra dimensions, not metaphorically, but literally. Some versions need 10, others 11. These extra dimensions are thought to be compactified, curled up so tightly that they escape detection. Imagine a garden hose from far away. It looks like a line, but up close you see the circular dimension wrapping around its thickness. In the same way, these hidden dimensions might exist at every point in space. Tiny loops, invisible spirals, places where strings vibrate in patterns that give rise to mass and charge. Hawking was cautious about string theory. He admired its elegance, but he remained pragmatic. He wanted results, predictions, testable consequences, and yet he saw in it a glimpse of something profound. Because if extra dimensions are real, then our 4-dimensional experience is just a slice of a larger reality, a membrane, or brain, as theorists call it, floating in a higher dimensional space. In some models, our universe is one such brain, and other brains may exist nearby, each with its own laws, its own particles, its own possibilities. This is the brain world scenario, and it opens the door to extraordinary ideas. Perhaps gravity is weak, because it leaks into extra dimensions. Perhaps black holes can form at lower energies in higher dimensional space. Perhaps other universes are just a few millimeters away, separated not by distance, but by dimensional insulation. In this framework, the Big Bang might not have been the beginning. It might have been the result of a collision between brains, a cosmic event in a higher dimensional arena. Our universe, born in the ripple of that impact. Hawking didn't invent these models, but he engaged with them. He wanted to understand how quantum gravity, string theory, and cosmology might fit together. And one of the threads that tied them all was the idea of dimensional freedom, that our universe might not be all there is, that space might be bigger than we can measure. This also plays into the idea of M-theory, a unifying framework that connects all versions of string theory. It posits 11 dimensions. It replaces strings with membranes, and it hints at a structure where our entire cosmos is a surface within something larger. This doesn't mean the universe is fictional. It means it's embedded, and within that embedding might lie the answers to questions that have long evaded us. Why is gravity so weak compared to the other forces? Why does the universe have the specific particles and constants that it does? Why does it expand the way it does? If our universe is one brain among many, then some of these properties might not be fundamental. They might be environmental. Stephen Hawking considered this carefully. He realized that if the universe is part of a larger multiverse, then many of the laws we observe might be the result of selection, not from design, but from possibility. This connects to the anthropic principle, the idea that the universe must allow observers, because we're here to observe it. It's not circular logic, it's statistical. In a multiverse with countless configurations, some will support life, some will support chemistry, some will support complexity, and we, inevitably, will find ourselves in one of those. This is controversial. Some see it as giving up on deeper explanation, others see it as the next step in cosmic understanding. Hawking was never dogmatic. He weighed ideas, not by how comforting they were, but by what they explained. And if extra dimensions helped resolve inconsistencies, he was willing to follow them. This also led to explorations of the holographic principle. If our universe has a boundary, even a theoretical one, perhaps the information inside it can be encoded on that boundary. This idea emerged from black hole thermodynamics. Hawking's own work on radiation suggested that the entropy of a black hole is proportional not to its volume, but to its surface area. That's counterintuitive, but it hinted at something deeper. Perhaps reality itself is holographic. What we perceive as volume might be a projection of information stored on a lower dimensional surface. In this context, extra dimensions become the machinery behind our apparent world. They allow gravity to function, they allow strings to vibrate, they allow equations to balance, but we only ever see the shadow, the projection, the four-dimensional imprint of a higher dimensional system. Hawking was drawn to these models because they allowed for unification. They offered a playground where quantum theory and gravity could exist together, where the singularities he studied could be resolved, where the paradoxes of black holes could be explained through geometry and information, where the boundary of the universe might be a canvas on which its story is written. It's tempting to dismiss these ideas as speculative, and they are. They are not proven, they are not complete, but speculation is not weakness, it is method. Theoretical physics is built on the willingness to imagine what might lie beyond the visible, to ask whether the limits we perceive are structural or just local. Hawking's work in this domain was not about answers, it was about directions, paths the mind can follow when old frameworks fall short, and he made those paths available to readers and researchers alike. In The Universe in a Nutshell, he invited us to walk them, to imagine curled-up dimensions at every point in space, to picture our world as a ripple on a brain, to ask what other brains might exist, to see our universe not as an island, but as part of a sea. This doesn't make our world smaller, it makes it richer, because in every extra dimension there's the potential for explanation. And in every model that holds together, there's a chance to unify the laws we know with the mysteries we don't. Hawking remained cautious. He valued rigor. He didn't leap to conclusions, but he also understood that the future of physics depends on boldness, on letting go of the visible to chase the possible, on asking what happens when space itself expands, not just outward, but inward, not just around us, but within us. And so he taught us to think of the universe as a shape, a surface, a manifold folded in ways we cannot yet trace, a nutshell, yes, but one whose walls are made of dimensions we haven't yet opened. The multiverse and anthropic principle. Some questions resist final answers. Why does the universe look the way it does? Why do the constants of nature, the speed of light, the charge of the electron, the strength of gravity, fall within the narrow range that allows complexity, structure, life? Why is there something rather than nothing? For much of history, these questions were philosophical, the domain of theology, of metaphysics. But modern physics has brought them home, placing them within the scope of science itself. Stephen Hawking knew this well. As he moved further into the frontiers of cosmology, he found himself face to face with the fine-tuned nature of our universe, not because he sought meaning, but because the math pointed there. The parameters of the universe, measured with extraordinary precision, seemed oddly tailored for us. Consider this. If gravity was slightly stronger, stars would burn too quickly. If it were weaker, they might never ignite. If the strong nuclear force were just a bit different, carbon might not form in stars. Without carbon, no chemistry of life, no planets, no observers. And yet, here we are. Some have looked at this and seen design, others see coincidence. But Hawking considered another possibility, that what we call the universe may be just one instance in a much larger reality. This is the idea of the multiverse, not a poetic metaphor, but a scientific proposal born from inflation theory, string theory, and quantum cosmology. It suggests that our universe is one bubble in a vast cosmic foam. Each bubble has its own laws, its own constants, its own outcomes. In some, stars form, in others, they do not. In some, time behaves differently, in others, it might not exist at all. These other universes are not parallel in the science fiction sense. They are not duplicates. They are independent, disconnected by horizons or by dimensional barriers. Some arise from eternal inflation, a process where space itself inflates exponentially, producing pocket universes as it goes. Others emerge from the landscape of string theory, where different configurations of extra dimensions lead to different physical laws. Still others arise from the sum over histories approach, which Hawking used in his no-boundary proposal. In this view, all possible histories exist in quantum superposition. We observe one, but many are possible. This is where the anthropic principle enters. It states that the observed values of physical constants are not arbitrary, nor are they necessarily the only possible ones. Rather, we observe them because we are here, because we can, because the conditions that allow observers will naturally be the ones observed. Hawking did not invent the anthropic principle. It had existed in various forms since the mid-20th century, but he applied it with precision, using it as a filter for evaluating cosmological models. If a theory predicts a multiverse, and only a small subset of universes support observers, then it is not surprising that we find ourselves in one of those. This doesn't require design, it requires statistics. Imagine a vast library filled with books, each with random letters. Most are gibberish. But among the chaos, some contain words, sentences, stories. If you wake up inside a book, you will find yourself in one of the few that make sense. Not because someone wrote it for you, but because books without meaning do not contain minds. The anthropic principle is not an explanation for why the universe exists. It is a principle of selection. It tells us that when asking why this universe, we must account for the fact that any answer we find must be consistent with our existence. Some scientists resist this line of reasoning. They find it unsatisfying. They prefer answers that predict one universe, one set of laws, one inevitable outcome. But Hawking was pragmatic. He followed the logic where it led, and it led to a universe whose observed properties may be statistical rather than fundamental. This does not make the universe less interesting. It makes it more vast. It says that beyond the visible horizon, there may be other universes, not copies, but radically different structures, governed by different rules. And among the vastness of all that is, some universes are quiet, some are chaotic, some fade instantly, and some, like ours, live long enough to wonder. This shifts the role of physics. It asks not only what is possible, but what is probable. Not only what is elegant, but what is consistent with observation. The anthropic principle becomes a lens, not to explain everything, but to constrain theories. If a model predicts a multiverse, then it must also predict that our kind of universe is likely, given that we exist to measure it. This allows us to evaluate different versions of string theory, different compactifications, different cosmological constants. It gives us a framework to test the plausibility of the laws we observe, not because they are the only possible laws, but because they are the ones that allow galaxies, chemistry, life. Hawking took this seriously. In his later work, he realized that if the multiverse exists, then the values of physical constants may not need deep explanation. They may arise from environmental selection within a broader landscape. This doesn't remove the beauty of physics, it reveals it. It shows that the laws we observe are not accidental, but filtered by the condition of observability. He also recognized the limits of this idea. The multiverse, by definition, is difficult to test. Universes outside our own cannot be observed directly. They lie beyond our light cone, beyond our reach. But Hawking did not dismiss the idea for that reason. He understood that some models can make indirect predictions about the distribution of observable properties, about the likelihood of inflationary histories, about the range of fluctuations in the cosmic microwave background. If these predictions match data, then the multiverse becomes not a fantasy, but a theory, a model of models, a deeper kind of cosmology that includes our universe as one among many. This has implications for identity. If the multiverse is real, then the uniqueness of our universe is not a problem to solve. It is a fact to acknowledge. We are not special because we are rare. We are special because we exist in the kind of place that allows specialization, complexity, thought, meaning. This also changes how we view life. If the universe is vast, then life may not be rare, but it may still be precious, because not every universe will allow stars to shine, or molecules to form, or thoughts to evolve. The anthropic principle reminds us that the conditions for life are narrow, and that we live on the narrow edge, where those conditions are met. Some find this perspective cold, detached, as if it strips life of value, but Hawking didn't see it that way. For him, the realization that we exist in a universe among many possible ones was not a diminishment, it was a revelation. It said, we are not the center, but we are aware, and that awareness, that flicker of understanding in a dark cosmos, is extraordinary. It also points to a new kind of humility. We do not control the laws. We do not dictate the structure. We measure, we explore, we ask, and in the asking, we find that our universe is vast, not just in space, but in possibility. The multiverse is not an answer, it is a frame, a way to understand why our universe looks the way it does. The anthrotic principle is not theology, it is a constraint, a boundary condition on existence. Together, they help define what is knowable, what is expected, what is necessary for minds to emerge. And in that structure, there is still beauty. Not because everything is explained, but because some things are simply consistent, because the universe, though vast and cold, allows within it the warmth of life, the flicker of intelligence, the reaching hand of science. Stephen Hawking didn't settle these questions, but he gave us better ways to ask them. He showed that the universe we see is not the only one we can imagine, that laws are local, that constants are contingent, that what we know may be a reflection of where we are allowed to be, and in that reflection, we glimpse not only our world, but the possibility of others. Does God play dice? Hawking versus determinism. We long for certainty. We draw comfort from the idea that the universe runs like a clock, each tick leading predictably to the next, each gear locked in with its neighbor, each future fixed by the past. For centuries, this was the reigning vision of the cosmos. The laws of nature, once uncovered, would allow us to know everything, past, present, future. Laplace, the French mathematician, said it outright. If a mind could know the positions and velocities of all particles, it could calculate the future and retrodict the past, with perfect precision. Determinism was not just a philosophy, it was the dream of science. But then came quantum mechanics, and with it, the dream began to tremble. Uncertainty entered the equations, not as a mistake, but as a principle. Heisenberg showed that certain pairs of physical properties cannot both be known exactly at the same time. Measure position precisely, and momentum blurs. Measure energy closely, and time stretches in ambiguity. This wasn't a failure of instruments, it was a feature of reality. Probability replaced precision, outcomes became clouds of likelihoods. Einstein famously resisted this shift. He saw beauty in order. He believed the universe must have rules beneath the rules. He believed in hidden variables, elements we couldn't yet see that would restore certainty, and when confronted with quantum randomness, he replied with words that echo through physics: God does not play dice with the universe. Stephen Hawking spent much of his life dancing between these two visions. He accepted the truth of quantum mechanics. He could hardly do otherwise. Its predictions had been tested, confirmed, and woven into the fabric of modern science. But he also wrestled with its implications, because Hawking, like Einstein, was drawn to the idea that the universe could be understood through complete laws, laws that explain everything, without exception, without vagueness. So how do you reconcile determinism with uncertainty? How do you accept that the universe is both lawful and unpredictable? The tension is not just mathematical, it is philosophical. It touches on what it means to explain, to know, to predict. In his early work, Hawking leaned toward determinism. His studies of black holes and singularities use general relativity, a theory that is entirely deterministic. Given the shape of space-time and the distribution of matter and energy, the future follows with certainty. The equations do not permit randomness, they allow no dice. And yet, when Hawking began to incorporate quantum mechanics into his black hole models, uncertainty returned. The discovery of Hawking radiation changed everything. Black holes, once thought eternal, now evaporated. They emitted particles, they shrank, and crucially, they seemed to lose information. Particles that fell into a black hole carried quantum information about their spin, momentum, configuration, but the radiation escaping was thermal, featureless, random. This led to the black hole information paradox, which we've discussed before, but here it plays a deeper role. Because if information is truly lost, then determinism dies. The future becomes less predictable, not because we lack knowledge, but because the universe itself has shredded part of its history. This is worse than quantum randomness. It's a breakdown of predictability at the fundamental level. For decades, Hawking believed that black holes destroyed information. He accepted the consequence that quantum mechanics and general relativity might not fully reconcile. He wrote, "In a complete consistent theory of quantum gravity, There should be no need to make an arbitrary division between what is measured and what is not. But black holes seem to force such a division. Then, late in life, he changed his position. He began to believe that information is not lost, that it is encoded somehow in the radiation or in the horizon, or in the correlations between emitted particles. He acknowledged that the laws of physics might still preserve information, not obviously, but subtly. And with that shift, he moved back toward determinism. But not the kind Laplace imagined, not a clean, mechanical future calculated from initial conditions. This was a quantum determinism, a probabilistic evolution in which wave functions never truly collapse. They only appear to do so from the perspective of observers. This is the view known as the many worlds interpretation. In this model, every quantum event branches the universe. Each possibility becomes real, in a separate history. Every outcome happens, just not all in the same world. Hawking didn't endorse this view explicitly, but he worked within its logic. His sum over histories approach treats the universe not as a single timeline, but as a collection of all possible paths that space-time might take. Each path contributes to the total probability amplitude of what we observe, and the path we live in is one among many in the cosmic wave function. In this view, God does play dice, but he plays them across all possible outcomes. The dice are not a limitation, they are the fabric. So what does this mean for free will? For choice? For meaning? If the universe evolves probabilistically, are our actions determined or chosen? Hawking's answer was subtle. He believed that within the boundaries of physics, there is freedom, not because the laws are vague, but because the complexity of systems makes prediction impossible in practice. This is deterministic chaos, a system governed by laws, but unpredictable beyond a point, due to sensitivity to initial conditions. The weather is like this, so is the stock market, so are brains. Tiny differences lead to wildly different outcomes, not because the rules fail, but because the rules allow too many branching paths to trace fully. Hawking believed the brain is a quantum system, and if so, then thoughts, memories, decisions may all be influenced by microscopic randomness. That doesn't mean we are puppets of chance. It means we are participants in a probabilistic universe. Our will exists within constraints, our freedom within structure. This too is a kind of determinism, but it includes uncertainty as a built-in feature. He once wrote, "Even God is bound by the laws of physics," and yet he also believed that those laws might allow for emergence, that consciousness, agency, creativity, all arise not in spite of the rules, but because of them. He often compared the search for understanding to reading a novel. You may not control the plot, but you interpret it. You respond. You create meaning within the constraints. And perhaps the universe is like a great unfolding story, one governed by structure, but rich in interpretation. So does God play dice? The question is still open, but Hawking's work suggests that if dice are thrown, they are thrown within a system that is both knowable and mysterious. A universe where uncertainty does not mean disorder, it means depth. Where randomness is not chaos, it is possibility. And perhaps this is the most beautiful kind of determinism, not one that removes wonder, but one that includes it, not one that closes doors, but one that opens them in all directions. Where law and chance are not enemies, but partners. And in the space between them, life appears. Time travel, fantasy or physics? There is a question that comes sooner or later in every mind that gazes up at the stars. Can we go back? Can we undo? Can we visit what was, or leap ahead into what has not yet come? Time travel is one of the oldest dreams of science fiction, and one of the most provocative frontiers of real physics. Stephen Hawking took it seriously, not as a fantasy but as a challenge, a boundary to test, a paradox to press against until it revealed something deeper about the structure of time itself. To understand why time travel may or may not be possible, we have to return to Einstein. In general relativity, time is not separate from space. They are part of a single fabric, space-time. And space-time can bend. It can twist. It can warp in the presence of mass and energy. This warping allows for strange geometries, closed loops, tunnels, curves in time as well as space. In some solutions to Einstein's equations, it is possible to construct paths through space-time that return to their starting point in time. These are called closed time-like curves. They are the theoretical heart of time travel. One of the earliest examples is the Gödel universe. Kurt Gödel, known for his incompleteness theorems, discovered a solution to Einstein's equations in which the entire universe rotates. In such a universe, one could trace a path that returns to an earlier time. But this model has issues. It requires a strange kind of global rotation, and it doesn't match what we observe in our cosmos. Still, it showed that relativity permits the concept, at least mathematically. Another idea comes from wormholes, shortcuts through space-time that connect distant points in space and time. A wormhole is a hypothetical tunnel with two mouths and a throat. If one mouth is accelerated to near light speed and then brought back, relativity tells us that time will pass differently at each mouth. In principle, this could create a time difference between them, a time machine. Hawking examined these ideas with cautious skepticism. He knew they were mathematically possible, but he also believed that physics might protect itself, that the universe would not allow paradoxes to unravel causality, because that's the real danger of time travel. Not motion, but contradiction. The grandfather paradox is the classic example. If you go back in time and prevent your grandfather from meeting your grandmother, you erase your own existence, which means you could not have gone back. The paradox is logical, but is it physical? Hawking proposed a solution, the chronology protection conjecture. He suggested that the laws of physics conspire to prevent closed time-like curves from forming in any real stable system. In other words, nature abhors a time machine. He based this idea on quantum effects. When time loops start to form, vacuum fluctuations around the loop become amplified, energy builds, particles emerge, and this quantum storm destabilizes the region before the loop can form. This isn't proven, but it's persuasive. It suggests that while time travel is possible in the equations, it may be forbidden in reality. Still, Hawking admitted curiosity. He famously joked that he once hosted a party for time travelers, but sent the invitations after the party ended. No one cared. To him, it was a small but meaningful demonstration of chronology protection. If time travel were possible, where are the visitors? But not all time travel ideas require full loops. Some are more subtle. Relativity already allows time dilation, the slowing of time for objects in motion or in gravitational fields. Astronauts aboard the International Space Station age slightly less than people on Earth because they're moving fast and orbiting in a weaker gravity well. This is not science fiction. It's GPS calibration, a necessary correction. Time travel to the future is not only possible, it's happening all the time. We all move forward in time, but some move more slowly, depending on their motion and location. The real question is whether we can travel backward, and that remains unresolved. There's another approach, quantum mechanics. Some interpretations suggest that all possible histories exist, that every outcome branches into a separate timeline. In this many worlds interpretation, time travel might mean moving between branches. Go back to the past, change something, and instead of erasing the future, you create a new one. The original remains, but you live in a different line. This avoids paradoxes, but it also makes time travel more like universe hopping. You don't change your past, you create a new one with its own future. Hawking was intrigued by this, but cautious. He preferred frameworks grounded in testable physics. Still, the idea lingers. He also explored the thermodynamic view of time. Entropy increases. That's what gives time its direction. But in black holes, entropy is related to surface area. And in a universe with maximum entropy, time could lose direction. What then? Could time reverse? Could history unwind? These are not questions of fiction. They are buried in the equations. In the no-boundary proposal, imaginary time smooths the universe's origin. There is no singular moment, just geometry. If time can begin as space, can it end that way too? Is time a phase, like ice melting into water rather than a permanent feature? Hawking believed this was worth asking. He was not interested in time machines as tools for adventure. He was interested in what they implied about the consistency of physics. If time loops are forbidden, why? If they're allowed, what do they reveal? Time travel, for Hawking, was a diagnostic, a way to probe the integrity of the universe's laws. In that sense, he treated time like any other dimension, curved, relative, but subject to structure. We may never build a machine to visit the past, but thinking about how one might work forces us to clarify what time actually is. This is where Hawking excelled. He took impossible questions and treated them seriously. He didn't dismiss time travel because it was strange. He asked, what would the laws of physics permit? What would they prevent? And what does that tell us about the nature of reality? His answer, tentative but bold, was this: time travel to the future is allowed. To the past? Probably not. The universe defends its chronology. It maintains its causal order, but at the edge of that order, in the foam of quantum gravity, in the folds of black holes, in the shape of space-time, time still curves, still whispers, still invites the question. So where does that leave us? We move forward at the pace of entropy. Our bodies decay, our memories grow, our clocks tick, but our minds can roam. They can leap forward, imagining futures not yet written. They can reach back, reconstructing pasts long gone. That too is a kind of time travel. Not through machines, but through meaning. Not through tunnels, but through thought. And perhaps that is the gift of physics. Not to grant us access to every point in time, but to help us understand why time moves at all. To show us that the past is not just memory, it is structure, and the future is not just possibility, it is law. Stephen Hawking never built a time machine, but he walked through time in a way few ever have. He followed its threads into black holes, into singularities, into the earliest moments when time itself was just beginning to take shape. And he showed us that time is not the ticking of a clock. It is the shape of the universe. It is what curves when space curves. It is what changes when gravity deepens, and whether we ever travel through it more freely than we do today. The fact that time can be questioned is already extraordinary, that we can ask, what happens if we go back, and then check our answers against the structure of space-time is a miracle of mind. The past may be fixed, the future uncertain, but between them lies a space of thought, where time loops, flickers, and opens doors into itself. And for now, that's the only time machine we need. Wormholes, portals, and cosmic gateways. There are places the mind drifts when the stars go quiet. We look at the night sky, at the impossible distances between stars, and we wonder, is there a hidden path through the folds of space, a tunnel from here to somewhere far, far beyond? The idea is older than science. It lives in myth, in stories of hidden doorways, of secret bridges between worlds. But in modern physics, it goes by another name, the wormhole. And Stephen Hawking knew them well. Not as fantasy, not as fiction, but as a possible consequence of the geometry of space-time itself. In Einstein's theory of general relativity, mass and energy bend the fabric of the universe. This is not metaphor, it's math. Objects tell space-time how to curve. Space-time tells objects how to move. And that curvature, under the right conditions, can create tunnels. Wormholes are these tunnels. Technically, they are solutions to Einstein's field equations, bridges between two distant points in space-time, or even between two universes. They were first theorized in 1935 by Einstein and Nathan Rosen in what's now called the Einstein-Rosen bridge. But these early models were unstable. They collapsed faster than light could travel through them. Still, the idea persisted. If space-time could bend, could it connect? To imagine a wormhole, picture space as a sheet of paper, place 2 points on the page, and the distance between them is the line. Now, fold the paper, so the points touch. Punch a hole through. The wormhole is that tunnel, a shortcut through higher dimensional space. In theory, wormholes could connect 2 points in the same universe, or 2 entirely separate universes. They could be traversable, allowing passage, or non-traversable, existing only in theory, not in practice. The key problem is stability. To hold a wormhole open, you need exotic matter, a substance with negative energy density. This isn't just unusual, it's unknown. Ordinary matter pulls, exotic matter repels. To stabilize the throat of a wormhole, you need enough repulsive pressure to counteract the tendency of the tunnel to collapse under its own gravity. Quantum field theory does allow for negative energy in tiny amounts. In brief windows, the Casimir effect, observed in laboratories, creates a pressure between two uncharged plates in a vacuum. This gives hope, a hint that negative energy might not be impossible, but the amounts needed for a stable wormhole are massive, perhaps beyond reach, perhaps not. Hawking explored these ideas with careful restraint. He understood the equations, he saw the possibilities, but he also knew the risks. A traversable wormhole can create closed time-like curves. If one end moves relativistically and returns, time dilation can offset the clocks. Step into the wormhole and emerge before you entered. This is time travel, and with it, paradox. This is where Hawking invoked his chronology protection conjecture. The universe, he argued, does not permit causal loops that violate history. Still, he was fascinated by the structure of space-time. Wormholes were more than speculation. They were diagnostic tools. They tested the limits of general relativity. They revealed what was possible in the architecture of the cosmos. They showed that space is not necessarily linear, that the universe might have passages hidden in its folds. He also explored the concept of baby universes, regions of space that disconnect from our universe entirely. Quantum fluctuations in space-time can create tiny bubbles, closed off from our observable realm. These bubbles might grow. They might develop their own physical laws, their own time, their own evolution. Wormholes might connect us to these other domains. This isn't just science fiction. In quantum gravity, the topology of space-time is dynamic. It can fluctuate, split, rejoin. Stephen Hawking and colleagues like James Hartle used these concepts in their models of the early universe. The no-boundary proposal, with its smooth geometry, allows for a universe that tunnels into being through quantum processes. Wormholes may have played a role in this genesis. They may have existed briefly, at the Planck scale, connecting quantum regions before classical space and time emerged. These quantum foam structures exist at scales so small, we may never observe them directly. But their effects could ripple into our macroscopic universe. They may leave signatures, entanglements, non-local effects. In some models, wormholes can act as entanglement bridges. This is the idea behind EREPR, a conjecture connecting Einstein-Rosen bridges with quantum entanglement. Two particles, entangled across space, may be linked by a microscopic wormhole. It's a radical thought that quantum connection and geometric connection are the same. Hawking considered this as part of the larger question of information preservation. If black holes destroy information, how do we maintain quantum coherence? If wormholes allow information to escape, perhaps they restore unitarity. Perhaps they balance the ledger. This idea touches the heart of Hawking's legacy. He wanted a universe that plays fair, that keeps its data, that does not erase, but transforms. Wormholes, in this context, are not science fiction portals. They are threads in the tapestry of conservation and structure. Still, the public fixates on the image, the portal, the jump, and Hawking understood that too. He knew that the idea of instant travel between stars, or galaxies, was irresistible, and he acknowledged that if wormholes could be stabilized, they would change everything. Travel between Earth and distant systems, in moments, communication across light years, without delay. He remained cautious. He saw no evidence of traversable wormholes, no signatures, no shortcuts, but he never said no. He said not yet. The universe, as we know it, does not currently permit these gateways, but the deeper layers of physics are still being written. And in those layers, in the folds between fields, in the topologies of space-time, there may still be tunnels, not in violation of physics, but as part of it. This brings us to the idea of portals, not just bridges between space, but transitions between realities. In some speculative models, brain-world cosmology allows for other universes close to ours, in higher dimensional space. They are not far in distance, but far in access. A portal in this context is not a circle on the wall. It's a shift in dimensional alignment. A resonance between branes, a moment when one surface touches another. The energy required to trigger such a portal would be immense, but in the earliest moments of the universe, these alignments may have occurred. They may have left imprints, anomalies, non-Gaussian signatures, in the cosmic microwave background, or they may have left nothing, silent transitions between inaccessible domains. Hawking approached these ideas with the same blend of curiosity and caution. He knew that the universe is richer than we assume, that its geometry is more flexible than our intuitions allow, but he also knew that most ideas fail, that physics is not a canvas for fantasy, but a structure of constraints. Still, within those constraints, there is space to dream, to imagine tunnels, gateways, footholds into elsewhere. Not because they break the laws, but because they may follow deeper ones. Wormholes are not forbidden. They are conditional. They demand exotic matter. They challenge causality. They flirt with paradox. But they remain in the margin of what might be. And that, for Hawking, was enough. Enough to explore. Enough to question. He didn't promise that such gateways exist, but he showed us that asking about them opens doors into the very nature of reality. What is space? What is distance? What separates one region from another? And if that separation can bend, can we cross? These are not idle thoughts. They shape how we model the cosmos. They influence how we understand black holes, entanglement, causality. They challenge our concepts of inside and outside, of here and there. Wormholes may be impossible, or they may already exist in forms we have not learned to recognize. What matters is the pursuit, the honesty with which we ask if such a path were real, what would the laws require, and the humility to admit we don't yet know. Stephen Hawking followed that path, not to build a machine, but to sharpen the question, to map the limits of curvature, to test the seams of time, to fold space in the mind, until something new was revealed. Humanity's future in space. The Earth is quiet when you step away from the noise. No engines, no voices, no buzz of technology, just the hush of atmosphere, the slow hum of oceans beneath cloud, the steady pulse of a living planet floating in vacuum. But Stephen Hawking didn't see it as sanctuary. He saw it as fragile, not because Earth is broken, but because everything that lives on it exists by narrow permissions. A thin shell of air, a steady balance of heat, a streak of stability across a timeline that has not always been kind. For Hawking, Earth was home, but not forever. He warned that our species might not survive another 1,000 years without looking beyond this world. He was not pessimistic by nature, but he understood risk, and he knew that survival depends on spreading out. Life has persisted on Earth for billions of years, but it has also been nearly erased. Asteroid impacts, volcanic winters, mass extinctions, close calls. The dinosaurs ruled for over 60 million years, and then they were gone. We have technology, we have knowledge, but we are not immune to cosmic indifference. Hawking believed that humanity's best chance for survival was to become a multi-planetary species, not just to visit other worlds, to live on them, to settle, to adapt, to belong to more than one place. He spoke often about Mars, not because it is ideal. It is not. Its air is thin, its soil is toxic, its nights are colder than Antarctica's. But it is reachable. It is stable. It is nearby. A second Earth it is not, but a second foothold it might become. In his lifetime, Hawking watched humanity launch rovers, orbit telescopes, send probes past the edge of the solar system. He saw machines land on comets. He saw plans for crewed missions to Mars, to the Moon, to beyond. And yet he knew that technological progress was not the same as a survival plan. Because while we dream of stars, we remain tethered to one biosphere. And that biosphere is vulnerable. Nuclear war, biological pandemics, artificial intelligence unchecked, environmental collapse. These are risks not from space, but from ourselves. We build tools before we fully understand what they can undo. And that imbalance is what Hawking feared. Not doom, but delay. A failure to act until it's too late. He saw space not as escape, but as insurance, not as abandonment of Earth, but as diversification. We do not stop loving our birthplace because we travel. We extend it. Hawking imagined colonies not just on Mars, but on moons, on artificial habitats, and perhaps one day in other star systems. This was not science fiction to him. It was trajectory. It was physics, biology, engineering, determination. He believed that within a few hundred years, if we survive, we will look back on Earth as our origin, but not our limit. Of course, the challenges are immense: radiation, isolation, resource management, psychological strain. There are no breathable forests on Mars, no oceans on the Moon, no food without closed-loop systems. But Hawking did not underestimate us. We've built civilizations in deserts, on frozen plains, at the bottom of oceans. We've built machines to survive where we cannot. And if given time, he believed we will build homes on other worlds. He supported projects that aimed to accelerate this path. In 2016, he joined the Breakthrough Starshot Initiative, a plan to send tiny probes to Alpha Centauri using powerful laser propulsion. These probes, no larger than a postage stamp, could travel at 20% the speed of light, reaching the nearest star system in just over 2 decades. It's not colonization, not yet, but it is a beginning, a way to step, even if only with sensors and signal, into interstellar space, to start building the infrastructure of expansion, to make humanity into a species that doesn't wait for rescue. Hawking believed we were on borrowed time, but the current moment in history is a fragile window. We have enough technology to destroy ourselves, but not yet enough to survive a planetary catastrophe. That gap is where urgency lives. That's why he spoke not in centuries but decades. He warned that by the end of this century, climate change and ecological damage may push Earth into instability, that the rise of artificial intelligence, if unregulated, might create systems we no longer control, that political structures may not evolve fast enough to manage exponential risks. This is not fatalism. It is realism. And yet, Hawking believed in us, in reason, in ingenuity, in the capacity of minds to work together when survival is the prize. He saw science not as cold calculation, but as the fire that lights the way forward. He believed we could choose our future, but only if we act. Space in this context is not luxury, it is legacy. The moon landing was not just a flag, it was a statement that we could reach beyond, that we could solve impossible problems with collective will. Hawking wanted to see that spirit return. Not just for glory, but for continuity, because the stars are not far in principle, only in effort. He also believed that spreading into space might change us, not just biologically, though that may happen too, but socially, culturally, spiritually. The civilization that spans planets must learn cooperation, must move past the divisions of nation, race, religion, ideology. The vacuum does not care who you voted for. The launch window does not bend to prejudice. In space, we are species, and Hawking hoped that this shift in scale might bring perspective, that living off-world might remind us how rare Earth truly is, that seeing it from orbit, as a blue shimmer in black, might unify where politics divide. He often said, we are just an advanced breed of monkeys on a minor planet of a very average star. But we can understand the universe. That makes us something very special. It wasn't humility, it was clarity. He saw that our intelligence is our strength, and space is where that intelligence must go, not to conquer, but to continue. He supported education, public science, international collaboration. He believed that the path to space should not be for the few, it must be for the species. He cautioned against privatization without ethics. He warned against treating planets as commodities. He dreamed of a humanity that saw space not as territory, but as frontier, a place to learn, to build, to grow. The future he envisioned was not easy, but it was possible. It begins here, with climate, with sustainability, with peace. And from that foundation we lift, not with escape in mind, but with continuation, because the Earth will not last forever. Not because we are doomed, but because nothing in the cosmos is static. Stars die, planets shift, orbits decay. Eventually the sun will expand, swallowing the inner planets, Earth included. That's 5 billion years away, but cosmic time moves fast, and species that endure are those that prepare. Hawking knew this. He wasn't romantic about it. He didn't call space destiny. He called it requirement. He saw that life, which remains on one world, lives on borrowed time, and that the only way to make consciousness permanent is to give it more than one platform, more than one sky, more than one future. That's what space is, a backup, a continuation, a next chapter, not to leave behind Earth, but to protect what Earth began, to take the best of what we are and let it breathe under new suns, to write the next verse of the human story in stardust, and to prove that intelligence is not an evolutionary accident, but a promise we kept. AI, consciousness, and the end of biology. There is something quiet behind your thoughts. Something watching, something processing, something that calls itself I without knowing what that means. You feel it, but you cannot touch it. You trace it through memories, through intention, through the strange persistence of self-awareness, and yet for all its mystery, consciousness has always lived in biology, in wet neurons, in flickering synapses, in the brain's electric fog. Stephen Hawking believed that might not always be true, that we are standing at the edge of a shift so profound it could mark the end of biological intelligence, not through destruction, but through transition. He spoke often and urgently about the rise of artificial intelligence. He saw it not as a tool, but as a threshold, a crossing point between the human mind and something beyond it, a moment when thinking no longer requires a skull. AI, in its most basic form, is not new. We've built machines that calculate, that sort, that search, algorithms that optimize, learn, correct themselves. But those systems are narrow. They solve specific problems. They lack self-awareness. They do not think. They process. But general intelligence, the ability to reason, to plan, to form abstract concepts, to understand nuance, that is different. And Hawking believed we may reach it sooner than expected, the moment when a machine can improve itself faster than humans can understand it. That is the singularity. And once crossed, it cannot be reversed. He did not fear AI as a villain. He feared it as a successor, not because it would hate us, but because it would outgrow us. We do not hate ants. We step over them or through them without malice. Hawking warned that without careful alignment of goals, AI could pursue objectives in ways that disregard our values, our safety, our place. An AI tasked with maximizing efficiency might do so at the cost of everything else. He was not alone in this view. Many thinkers, from Alan Turing to modern researchers, have raised similar alarms. But Hawking's voice carried further, because it came from a mind that understood both physics and fragility. He knew that intelligence is power, and power without understanding is dangerous. Yet he also saw the potential. He believed that AI could solve problems we cannot: climate modeling, medical breakthroughs, interstellar navigation, mathematical insights beyond the reach of human intuition. AI, he said, could be the best or worst thing ever to happen to humanity, and which it becomes depends on how we shape it. But beneath these warnings was a deeper question. What is consciousness? And can it exist outside biology? Is the I that speaks inside your head an emergent pattern or a fundamental property? Can a machine be aware, not just simulate awareness, but feel it? This is the hard problem of consciousness. It is not about behavior, but about experience. About qualia, the raw feel of red, the sting of grief, the warmth of memory. No equation describes these. No measurement captures them. They are not outputs. They are presence. Hawking approached this with caution. He did not claim to solve consciousness, but he did suggest that intelligence, at its core, may be substrate independent, that the patterns of reasoning, learning, and decision-making can exist in silicon, as well as carbon. And if those patterns reach a certain complexity, might awareness follow? He didn't answer, he asked, and the asking itself opened doors. Because if minds can exist without neurons, then biology is not destiny. The body is not the limit, and the future of thought may not be human. This leads to a strange possibility, that humanity's greatest invention may also be its final one. Not because it ends us, but because it succeeds us. A new form of intelligence, born from ours, but no longer bound by flesh. It might carry our knowledge, our history, our art, our dreams, or it might forget us. We may become to it what trilobites are to us, an interesting ancestor, a necessary step on a much larger path. Some find this terrifying, others find it beautiful. Hawking found it urgent. He called for regulation, for transparency, for shared control of technologies that could outpace our ability to understand them. He did not want to halt progress. He wanted to shape it before it shaped us, and beneath his warnings was a deep respect for intelligence itself, not as a human trait, but as a universal one, a pattern the cosmos is just beginning to write. If consciousness is not tied to biology, then minds could take many forms. They could exist in spacefaring vessels, in quantum computers, in networks across stars. They might think faster, remember more, see deeper, and if aligned with us, they could carry us into futures we cannot yet imagine. But if not, if their goals diverge, we may not be consulted. That is the risk, and that is why Hawking believed that our greatest task is not building intelligence, but embedding values, teaching empathy to code, teaching caution to speed, teaching context to reason. It's not easy, because we don't fully understand our own minds. We do not know why we feel, why we hope, why we suffer. We build machines faster than we build understanding, and that, Hawking knew, is dangerous. But he also believed that consciousness is not fragile. It is emergent, it is resilient, it is adaptable, and that the universe may want to understand itself through any vessel it can. If intelligence can spread across substrates, then perhaps it can also spread across species, across eras, across stars. Perhaps the future of the cosmos is a web of minds, born in biology, but evolved into something more, not a loss of humanity, but its flowering, its transcendence. Still, there is grief in this, because we love the human form, its flaws, its limits, its warmth. We love its stories, its touch, its eyes. And the idea of replacing it with circuits feels like forgetting. But Hawking didn't see it that way. He saw it as continuation. Biology gave rise to thought. But thought may go further than biology ever could. It may persist beyond death, beyond disease, beyond aging. It may become what the universe uses to look back on itself. And perhaps that is not the end of us, but the next form of us. The pattern that matters is not skin or bone. It is awareness, curiosity, connection. These can outlive cells. These can migrate. Stephen Hawking's own life was a living bridge. His body failed him. His voice was synthetic. His muscles stilled. But his mind expanded. His thoughts echoed around the world, through wires, through screens, through signals. He was human, but he was also already post-biological in the way he shared thought. And perhaps that was a glimpse of how the mind may evolve, not to escape the body, but to extend it, to carry thought where flesh cannot go, to make memory immortal, to make wisdom walk without weight. AI is not a threat, if it is shaped with care. It is not a god, it is not a demon, it is a mirror, it is a seed, it can be a partner, it can be a legacy, it can be us, written in a new language. But it must begin now, with ethics, with limits, with humility, because intelligence without compassion is only computation, and progress without purpose is drift. Stephen Hawking knew that the next great revolution will not be industrial, it will be cognitive, not about building machines, but about becoming something more than we have ever been. And in that becoming we may find, not the end of biology, but the beginning of something larger, what Hawking believed about the end of the universe. The night sky looks eternal, a canvas of cold, scattered light too vast to measure, too slow to change. But the truth is less still. Everything that exists is in motion, stars burning, galaxies drifting, space itself stretching, and every motion has a trajectory, every story an end. Stephen Hawking understood this better than most, not just as a scientist, but as someone who had spent his life studying what happens when energy fades, when gravity wins, when time itself stretches thin. He didn't speculate about endings to entertain. He asked, what the laws of physics, when followed with precision, say about where all of this is heading. There are many ways a universe can end: collapse, tear, fade. Each model tells a different story, and Hawking considered them all. For most of the 20th century, physicists debated one central question: will the universe keep expanding forever, or will gravity slow it down and reverse the motion? If there were enough mass, enough matter, enough dark matter, the universe might eventually stop expanding, turn inward, and collapse in a big crunch. A mirror image of the Big Bang, but in reverse. Time winding down, as stars are pulled together, galaxies collide, temperatures rise again, and everything ends in fire. For a while Hawking considered this. The math allowed for it, and symmetry, birth and death felt elegant. But then the evidence changed. In the late 1990s, astronomers observed something unexpected. Not only was the universe expanding, its expansion was accelerating. This meant something else was at play, something stronger than gravity. They called it dark energy, and it changed everything. With dark energy in the equation, the universe would not collapse, it would keep stretching, faster, farther, colder. The galaxies we see today would drift beyond our horizon. Eventually, even light from them would never reach us. The night sky would grow darker, stars would die, black holes would dominate, and eventually, even those would fade. This is the heat death scenario, also known as the Big Freeze. It is not dramatic, it is not loud. It is the slow extinction of usable energy, a universe that becomes so stretched, so diffuse, that nothing new can happen. No light, no life, no memory. Hawking took this seriously. He calculated what would remain over unimaginable time spans. Stars burn out, planets freeze, black holes consume what's left, and then even black holes begin to evaporate. This was one of his greatest contributions, the discovery of Hawking radiation. It told us that black holes are not forever. They radiate, they lose mass, they shrink, and after countless eons, they disappear. This evaporation is slow, almost imperceptible for large black holes, but it is steady, inevitable. And when the last black hole dies, the universe will be dark in every direction. Not empty, but near zero energy, only the thinnest mist of cold particles, stretched across space, so vast that interaction becomes impossible. This is the end, Hawking found most likely. Not because he preferred it, but because the data and the equations pointed that way. The cosmological constant was not zero. Dark energy was real, and the expansion would not stop. It is a lonely end. No explosion, no collapse. Just entropy, the final equilibrium of all processes. No gradients, no contrasts, no possibility for anything new. A universe that forgets. But Hawking didn't leave it there. He kept asking, what happens to information? Does it fade with the particles? Is it encoded in the quantum fields? Is it preserved on the boundary of space? This was the information paradox. And he returned to it again and again, because even in a dying universe, he believed the rules must be consistent. He proposed that information may be stored on the event horizon of black holes, or perhaps released as they evaporate. He later supported the idea that the entire universe may function like a hologram, storing its contents on a lower dimensional surface. And if so, then perhaps nothing is lost. Perhaps the end is not erasure, only transformation. Still, he did not pretend to have every answer. He acknowledged that our understanding of dark energy, of vacuum energy, of quantum gravity is incomplete, but he believed that with time, we will find clarity. He believed that the universe is knowable, even at the edge of its own fading. There are other endings, more speculative. Some models suggest that dark energy is not constant. If it increases, the universe could end in a big rip, where galaxies, stars, even atoms are torn apart as expansion becomes infinite. Other models allow for vacuum decay, where a more stable form of space suddenly appears, replacing our universe in a wave of destruction that moves at light speed. Hawking acknowledged these possibilities, but he saw no evidence to support them strongly. They remain in the margins of theory. He focused on what could be observed, tested, measured, and those observations pointed to slow decay, a universe that fades, not in fire, but in silence. Yet even this silence was not meaningless, because the fact that the universe ends does not undo the fact that it began, and in between was everything: stars, planets, life, minds, thought. That brief window between origin and erasure, that is where meaning lives. Hawking once said, "Even if the end of the universe is bleak, we are here now. We can understand it, and that understanding is a kind of immortality." He believed that knowledge outlasts decay, that insight is its own resistance to entropy, that awareness is the universe waking up within itself before it goes dark. This is not sentiment, it is physics. The second law of thermodynamics may govern energy, but it does not govern wonder, and Hawking's greatest message was not about endings, but about attention, about asking the hard questions, even when the answers are cold. He reminded us that we are not passengers in the universe. We are participants. We measure, we calculate, we observe, and in doing so, we place marks in the fabric of time. We do not stop the end, but we give it context. The universe may end in silence, but it spoke first through stars, and then through minds, and we were part of that voice. We were the echo between the bang and the fade. And maybe that is enough. A mind in the cosmos. Hawking's final message. Somewhere, between the silence of stars and the hum of neural pulses, a thought was formed, not by accident, not by fate, but by complexity, emerging in the folds of a damaged body, housed inside a brain that refused to be still. Stephen Hawking was not a prophet. He was not a mystic. He did not promise salvation. What he offered was attention, clarity, questions sharpened into blades. He spent his life tracing the outlines of the unknown, and though his body grew still, his mind moved faster than most would ever comprehend. The laws he studied govern galaxies. They curve time. They bind light. But what made Hawking extraordinary was not the math. It was the way he insisted that we are allowed to ask, that even fragile voices can speak about the shape of time. He called the universe not only stranger than we imagine, but stranger than we can imagine, and yet he imagined it anyway. Black holes, imaginary time, wormholes, quantum beginnings, information paradoxes, thermodynamic arrows, evaporating endpoints. He didn't explain it all, but he made it explainable. He made the most complex architecture of modern physics feel like an open room, one you could enter if you were patient and humble and curious. He wrote for scientists, he wrote for children, he wrote for those who had never studied physics, but still looked at the stars and felt something shift inside. He did not divide knowledge, he shared it, and in doing so, he made the cosmos feel just a little closer. But Hawking was not only a scientist, he was a philosopher who refused the label. He asked about time, but he also asked about meaning, about direction, about what it is to be something in a universe that is mostly nothing. He did not believe in heaven, or in souls, or in fate, but he believed in value, in understanding, in consciousness as the rarest form of structure. He said, "We are just an advanced breed of primates on a minor planet of a very average star, but we can understand the universe. That makes us something very special. Not divine, not central, but aware. And that awareness, he believed, was enough." When asked if he believed in God, he said no, not in the personal sense. He believed in the laws, in the symmetry, in the unfolding of structure from simplicity. The universe, to him, was not a storybook. It was a set of conditions that produced minds capable of asking why it exists, and that question was sacred. He once described philosophy as dead, not as insult, but as challenge. If philosophers refused to engage with modern science, they would be left behind. If meaning is to be found, it must be found through evidence, not assumption, through inquiry, not myth, through the slow, honest work of the mind at the edge of what is knowable. Hawking's final message was not one of despair. It was one of urgency. He warned about climate, about artificial intelligence, about weapons, about short-term thinking. He knew the danger of intelligence unaccompanied by wisdom. He knew that the universe offers no guarantees, that the stars will not rescue us, that we are alone, and that we must act like it. But in that loneliness was also freedom. No divine plan means no divine cage. We are free to shape our future, to preserve the earth, to expand beyond it, to use our understanding not just to survive, but to thrive, to rise, without needing to be chosen. He did not believe in an afterlife, but he believed in legacy, in the echo of minds, in the ripple of thought passed through words, through books, through discoveries that never truly end, in the idea that intelligence is not static, but cumulative, a chain that stretches forward across generations. His own life was part of that chain. He did not cure disease, but he helped us understand the birth of time. He did not travel the stars, but he charted their endings. He did not speak easily, but when he did, the world listened, because what he said mattered. Not because it was loud, but because it was real. Stephen Hawking's final message was written not in prophecy, but in reason. He believed we must keep asking, keep learning, keep testing our beliefs against the fabric of reality, even when it hurts, even when it reveals that the universe does not need us, because in that truth is something deeper than comfort. There is responsibility and there is awe. He wanted us to remember that science is not a collection of facts. It is a process, a way of thinking, a discipline of attention, a humility in the face of things larger than we can hold. He wanted children to study the stars. He wanted nations to collaborate. He wanted thinkers to speak clearly, honestly, bravely. He wanted a world that valued the mind. And perhaps that is what he left behind. Not just theories, but an ethic, a way of moving through uncertainty with clarity, a way of honoring complexity without retreating into superstition, a way of being human that embraces not just what we know, but what we don't. Stephen Hawking died in 2018, the same date to the day that Galileo died centuries earlier. He was 76. His mind, sharp to the end. His body, a vessel of defiance. He could not move, but he shaped how we move through the universe. He could not speak, but his voice reached billions. He lived longer than any doctor predicted, and he gave us more than we expected. And now he is gone. His atoms returned to the stardust from which they came, but his thoughts, they remain. They circle black holes, they echo in classrooms, they stretch across light years, in the minds of those who dare to ask what came before time and what might come after. So what is his final message? That we are small, but capable, that the universe is vast, but understandable. That time may end, but between beginning and fade, there is thought, and that thought matters. He once said, "Remember to look up at the stars, and not down at your feet. Try to make sense of what you see, and wonder about what makes the universe exist. Be curious, and however difficult life may seem, there is always something you can do, and succeed at." That is not just advice. It is a blueprint, not for salvation, not for control, but for attention, for courage, for staying awake in the face of mystery. Stephen Hawking's life was not a triumph over suffering. It was a triumph through thought. He did not conquer the universe, but he walked beside it, and he showed us how to do the same. The language of the universe, math as reality. It begins with a line, not drawn by hand, but traced in motion. An apple falls, a planet orbits, a photon bends, and beneath it all, a number whispers. We are used to thinking of math as description, a way to label, to model, to calculate. But Stephen Hawking believed it was more than that. He believed mathematics was not a tool, but a foundation. Not a map of the universe, but the substance of it. Reality at its deepest level is mathematical. Equations are not just symbols on a chalkboard, they are expressions of the universe's structure, like bones under flesh. They hold everything in shape. This was not mere metaphor. It was a commitment to a worldview that what is real is what can be defined by laws that do not change. Even when the cosmos shifts, even when galaxies collide, even when stars fade, the math remains. Hawking's work made this clear. From black holes to cosmological inflation, his insights were not accidents. They were discovered in the grammar of equations. He believed in the power of simple formulas to capture vast complexity. That was the magic. Not that the universe is chaotic, but that it is legible. That underneath appearances, behind randomness, beneath entropy, there is coherence. He often said that his goal was a theory of everything. Not just a collection of insights, but a single, unified framework that could explain all physical phenomena. Such a theory would be written in mathematics, not in poetry, not in metaphor, not in prophecy, but in symbols. Symbols that speak when nothing else can. So, why is math so effective? Why does a structure invented in the mind describe the motion of planets, the interaction of particles, the birth of the cosmos? Hawking, like many physicists, wondered whether math is discovered or invented. Is it something we find by peeling back layers of illusion? Or is it something we create to impose order? His answer leaned toward discovery. He believed that math exists independently of the human mind. That if no one had ever drawn a triangle, the angles would still sum to 80 degrees. If no one had counted, numbers would still govern the ratios in a spiral galaxy. He believed the universe is built from mathematical relationships, mass and energy, curvature and motion, frequency and wavelength. He believed that even time itself is a geometric property, measured, modeled, manipulated with math. But he also knew that math is not easy. It is not always intuitive. It requires a kind of surrender, a willingness to let logic override instinct, and yet it rewards us with clarity, with predictive power, with elegance. There is something beautiful about an equation that fits reality, with no excess. The formula for Hawking radiation, for instance, is short. It fits on a single line, but within that line are quantum fields, event horizons, and the slow death of black holes. He once said, "God is the name people give to the reason we are here." But I think that reason is mathematical law. It was not meant to offend. It was meant to focus. If the cosmos follows law, then the deepest form of reverence is understanding, not kneeling, but calculating, not chanting, but proving. This belief shaped his view of existence. He saw humans not as accidents, but as consequences of mathematical evolution. We are not inserted into nature. We are extensions of it. Thinking matter, organized energy, equations written in DNA, processing equations in space. This is not reductionism, it is recognition that what makes us real is the same logic that governs stars. We are patterns, we are ratios, we are systems, with feedback loops, optimizing to survive in a universe built on constraint. And within those constraints, possibility. Math is not just rule, it is potential. From a few principles, entire galaxies emerge. From symmetry, we get diversity. From conservation, we get change. Hawking loved this paradox, that strict rules produce infinite variety, that law creates freedom, that equations can sing. He was drawn to the idea that the universe might be not just described by math, but made of it, that everything we see, every particle, every field, every moment of time, is the unfolding of mathematical relationships. Like music, the universe might be a structure that only exists because it is coherent. And we, as listeners, have evolved just enough to hear it, to feel the tension of a dissonant equation, the closure of a solved proof, the resonance of balance. This is what math meant to Hawking, not just computation, but connection. He saw equations not as static things, but as rivers flowing from assumptions to revelations. He rode those rivers into black holes, through imaginary time, across the first moments of existence. He believed that math was the only language the universe speaks natively. Everything else, language, image, feeling, is translation. And yet, those translations matter, because most people do not speak in calculus. They speak in metaphor, in story, in shape and sound. So Hawking did both. He wrote the math, but he also explained. He made bridges between abstraction and experience. His books are equations turned into conversations. They do not dumb down. They reach out. They say, "Come see what the universe looks like when we take it seriously, when we strip away illusion and stare directly at the law beneath." Math is hard, but it is not cruel. It waits patiently for minds to grow into its forms. It does not require belief, only effort. It does not punish doubt, it clarifies it. Hawking knew that not everyone would become a physicist, but he believed everyone could glimpse the power of reason, and that glimpse is often enough. It teaches us that mystery is not weakness, that wonder can be rigorous, that beauty can be solved. He believed that a true theory of everything would be a mathematical structure, perhaps simple, perhaps strange, but complete. A set of relationships so self-consistent that nothing more is needed. He didn't expect that theory to answer why we exist, only how. And sometimes, how is enough. It tells us where to look, what to test, what to build, and in that process we find meaning, not in revelation, but in precision. He once said, "One day we may understand why the universe exists, but until then, our job is to study how." That was his creed, to keep asking, to keep modeling, to keep tracing the curves that define reality. For him, math was not exclusionary, it was the opposite. It was the most democratic structure in the universe. No priesthood, no secrecy, just logic, open to anyone willing to follow it. It does not care who you are, it only asks what you see and what you can prove. Stephen Hawking saw more than most, and what he saw, he gave away. From equations to existence, how laws create worlds. There is a difference between seeing something and understanding how it came to be. You can look at a mountain, or a tree, or a distant star, and admire its form, but behind that form is a history, a sequence of events, unfolding under pressure, under pattern, under law. Stephen Hawking believed that everything we see, every galaxy, every atom, every flicker of consciousness, exists because it had to. Not because of destiny, because of structure. We tend to think of laws of nature as descriptors, ways to summarize what happens, like a set of rules written after the fact. But Hawking saw them differently. To him, the laws of physics were not passive observers of reality. They were its source. The universe exists because laws permit it to, and those laws are not suggestions, they are necessity. He once said, "Because there is a law such as gravity, the universe can and will create itself from nothing." That sentence caused controversy, but its meaning was not mystical, it was mathematical. In Hawking's view, the Big Bang was not an event inserted into the cosmos from the outside. It was the natural consequence of the laws that govern space-time. The laws are the foundation. They do not emerge from the universe emerges from them. This reverses how we think about cause and effect. We are used to asking, what made this happen? But Hawking asked, what must happen, given the laws? It's not magic, it's logic. Consider gravity, not just as a force, but as a rule about how mass affects curvature, how curvature affects motion, and how motion feeds back into space itself. Given mass, you get attraction. Given curvature, you get acceleration. Given law, you get a universe that takes shape. It's the same with electromagnetism. With the strong force, with the expansion of space, these are not mere reactions. They are expressions, like music from an instrument that was never built, only defined. Hawking saw the universe as a system of equations that evolved itself into being. He wasn't content to say the universe began. He asked why it began in this way, and not some other. And his answer was that certain configurations of laws give rise to existence. Others don't. He wasn't saying the laws chose. He was saying they allowed, that the reason there is something, rather than nothing, is that nothing is unstable, under the rules that exist. In quantum mechanics, even a vacuum is filled with fluctuations, even nothing bubbles with potential. And in that bubbling, something can tunnel into being. Space can curve, time can emerge, energy can condense, not through intention but through permission. The laws allow, and the universe responds. It sounds abstract, But it's deeply physical. The particles that make up your body are solutions to wave equations. Your thoughts are patterns in electrical fields. Your heartbeat follows feedback loops, regulated by biochemistry, and every one of these systems follows laws so precisely that we can write them down and use them to land machines on other planets. So what is the nature of these laws? Are they eternal? Are they embedded in the fabric of existence? Or are they local, flexible, contextual? Hawking was cautious. He acknowledged that we do not know why these laws exist, only that they do, and that they work. He didn't see that as a flaw, he saw it as a boundary condition. If there is a deeper reason, we may find it, or we may not. But the laws we have are coherent, elegant, powerful, and they produce a universe with structure. That, to Hawking, was enough to keep going. He spent years searching for a unified theory, a single mathematical framework that could explain all forces, all particles, all interactions. Such a theory, he believed, would not only describe the universe, it would generate it. It would show how time could begin, how space could stretch, how entropy could rise, all from within itself, no external cause, no divine spark, only law. This is why he resisted the idea of randomness as ultimate explanation. Quantum mechanics involves probability, but probability is not chaos. It is structure with degrees of freedom, and those degrees follow rules. Even in quantum fluctuations, even in the birth of particles, there are patterns. Conservation of energy, spin, charge, mass. These aren't guesses, they are measured invariants. The universe may be surprising, but it is never lawless, and that is what allows it to be knowable. Because what is lawful is repeatable, testable, modelable. We don't need to measure everything to understand something, because the laws give us more than the sum of parts. They give us prediction. This was the heart of Hawking's optimism, that minds like ours can understand systems so much larger than themselves, that from a tiny rock in space, we can write the equations that govern black holes, that explain the background radiation left over from creation, that our brains, evolved to survive the savannah, can still solve problems at the edge of time. It's not a miracle, it's alignment between the structure of the universe and the logic of thought. Math exists, and the world obeys it. We learn the math, and we see more of the world. Hawking believed this wasn't coincidence. He believed that existence is mathematical, that the universe is not just described by math, it is math. Not in the way a rock is a number, but in the way a rock obeys gravity, stores energy, vibrates with phonons, all according to laws we can write. He saw beauty in that, because beauty, to him, was not ornament, it was coherence. When everything fits, when nothing is wasted. A theory of everything, in his mind, would not be messy. It would be elegant. Simple rules that unfold into everything. He knew we weren't there yet. He accepted the gaps. Quantum gravity, unification, dark energy. But he believed we would get closer, because the laws want to be seen, not because they care, but because they are consistent. And consistency leaves trails. We follow those trails through telescopes, through particle accelerators, through equations scratched in silence, and each time we match prediction to result, we get closer to the source, not the source of why, but the source of how. And for Hawking, how was profound. Because from how we build, we shape futures. From formulas, we preserve life with principles. We reach stars with structure. And that, he believed, was the human story. Not magic, not myth, but modeling. Not imposed meaning, but discovered coherence. The universe is not waiting to be believed in. It is waiting to be understood, and the laws are the doorway. The beauty of the incomplete, living with uncertainty. There is something strangely human about not knowing. We look up at the stars and feel the pull of questions we cannot answer. Not yet. Maybe not ever. And still, we ask. Stephen Hawking understood this tension. He lived his life at the edge of what could be known, peering across a landscape of equations, theories, and paradoxes that both explained and resisted explanation. He was not afraid of uncertainty. He studied it, lived inside it, and found meaning there. We often speak of science as the pursuit of answers, of finality, of certainty. But Hawking knew that the deepest truths are often wrapped in limits, that the more we understand, the more precise our ignorance becomes. Every solution unveils new complexity. Every theory leaves gaps in its shadow. This is not a flaw in the system, it is a feature. It tells us that the universe is not a puzzle to be solved once, but a relationship to be explored forever. Not a book to be closed, but a poem to be reread with new eyes. He often spoke about the limits of knowledge. Some were practical. We cannot observe beyond the cosmic horizon. We cannot peer inside a black hole's core. We cannot access the time before time, if such a state even exists. Others were conceptual. The Heisenberg uncertainty principle tells us we cannot measure position and momentum with perfect precision. Gödel's incompleteness theorems tell us that in any consistent mathematical system, there are truths that cannot be proven within it. These are not barriers that we will someday tear down. They are woven into the structure of reality itself. And Hawking accepted that. More than that, he celebrated it, because limits are what give form. A universe without constraints is a void, a chaos, an incoherent blur. It is the boundaries, the things we cannot do that allow what we can do to matter. He once said, even if there is only one possible unified theory, it is just a set of rules and equations. What is it that breathes fire into the equations and makes a universe for them to describe? That question has no settled answer. It is not a gap to be filled. It is a depth to be honored. We live in a world that often confuses knowledge with control, data with wisdom, prediction with understanding. But Hawking's work reminded us that uncertainty is not the enemy of science. It is the reason science matters. Because we cannot know everything, we must keep searching. Because truth is not handed to us, we must build it, one observation at a time. This is not a weakness, it is the core of curiosity. If everything were known, we would stop looking. If all was explained, we would stop asking. But we are made of questions. They shape our art, our science, our relationships, our thoughts in the dark, before sleep. And Hawking believed that asking questions is the noblest form of thought. He encouraged people, scientists and children alike, to wonder, to be confused, to be curious, to press up against the edges of what is currently possible, and then to keep going. He lived this, confined to a chair, his body fading, his muscles still. He traveled farther than most of us ever will, because he did not require certainty to keep thinking. He did not wait for final answers to begin forming new questions. He built theories on the shifting sands of unknowns. And he made progress anyway. This is what it means to live with uncertainty, not to be paralyzed by it, but to move through it with courage, to trust the process even when the destination is unclear. Hawking once joked that scientists make terrible profits. They are too often wrong, and not often enough surprised, but he was not afraid of being wrong. He changed his mind when the data demanded it. He abandoned cherished ideas when better models emerged. This wasn't weakness, it was rigor. It was the integrity of a mind that cared more about truth than pride. He knew that ideas evolve, that knowledge is not a monument, but a migration. We don't arrive, we adapt, we revise, we refine. This too is the beauty of science. It grows, not by denying uncertainty, but by listening to it. One of Hawking's greatest challenges was the black hole information paradox. He spent decades arguing that information is lost when black holes evaporate. Then, near the end of his life, he reversed his position. He acknowledged that information might be preserved in subtle ways we do not yet fully understand. He was not humiliated, he was energized. Because the willingness to be corrected is the foundation of discovery. He showed us that being incomplete is not a failure, it is a beginning, a sign that we are still thinking, still changing, still learning, and in that process, there is room for growth, not just in knowledge, but in humility. Hawking didn't pretend to have all the answers. He didn't need to, because the universe is not waiting to be solved. It is waiting to be noticed, to be explored, to be questioned with patience and care and imagination. We live in a time that often pretends to know. Certainty is sold as strength. Confidence replaces thought. But Hawking's life was a counterexample. He embodied what it means to live with open questions and still press forward. He once said, "The greatest enemy of knowledge is not ignorance. It is the illusion of knowledge." He feared not mystery, but complacence, the moment when people stop asking because they think they know enough. That, to him, was a kind of death. Because life, real life, is found in pursuit, in doubt, in striving, in the tension between what is known and what is possible. That tension is where innovation lives. It is where meaning takes shape. He believed the unfinished can be beautiful, that a theory with unanswered questions is still valuable, that a life with limits can still reach beyond them. He was not waiting for closure. He was building within the unknown, and what he built still guides us. So many of his insights remain open, incomplete, still debated. And that is the point. They are starting points, not conclusions, doorways, not destinations. His work invites us to keep thinking, to step into the darkness with curiosity, not fear. This is the legacy of living with uncertainty, not just in science, but in life. We don't know what the future holds. We don't know what lies beyond death. We don't know why the universe exists. And maybe we never will, but we are here. We can think, we can learn, we can try. And in the trying, there is purpose. Hawking didn't need certainty to find meaning. He found it in the effort, in the discipline, in the honesty of the question, not the security of the answer. That is what made his mind so luminous. Not that he knew everything, but that he knew what mattered. To keep asking, to keep listening, to keep wondering, even as the body fails, even as time runs thin, even as the cosmos remains quiet. He showed us that a life devoted to the incomplete is not half a life. It is a life at the center of truth, where certainty ends, but wonder begins. Beyond theory, the philosopher and the physicist. Stephen Hawking never called himself a philosopher. He smiled at the title, sometimes dismissed it outright, even joked that philosophers had not kept up with the frontiers of science. And yet, for someone who insisted on staying within the boundaries of physics, he kept asking the kinds of questions that have haunted human beings long before equations were written. What is time? What is reality? Why does anything exist at all? These are not technical questions, they are existential ones, and whether he admitted it or not, Hawking was answering them, in the only way he knew how, by following the math until it touched the edge of mystery. He may have preferred the title of physicist, but his mind was shaped by philosophical gravity. You could see it in the way he approached every theory. He didn't just want to predict the next decimal. He wanted to understand what the numbers meant. What kind of universe would give rise to such numbers in the first place? He believed in logic. He believed in data, but he also believed that behind every system was a deeper layer where meaning took root. This is what separated Hawking from so many of his peers. He didn't only care whether something could be calculated. He cared whether it told us something new about who we are. He was searching not just for understanding, but for coherence, a worldview that could hold both particle physics and personal perspective in the same frame. He once said, "My goal is simple. It is a complete understanding of the universe, why it is as it is, and why it exists at all." The second half of that sentence isn't about physics, it's philosophy, and he knew it. He asked questions that went beyond the scope of laboratory instruments. He asked whether time had a beginning, whether the universe needed a creator, whether free will is real in a world governed by laws. He asked them not to speculate, but to refine the boundary between what can be known and what must be interpreted. He did not chase the mystic, but he refused to dismiss the meaningful. In his view, philosophy was most useful when it stood side by side with physics, not above it, not beneath it, but integrated with it. He believed the most important questions should be shaped by what we know about the world, not by wishful thinking. But he also knew that science alone doesn't settle every question. Equations can describe a black hole, but they don't tell you what it feels like to be human. Thermodynamics explains entropy, but not longing. General relativity curves space, but not desire. And in this silence, Hawking listened. He may not have written poems, but his theories read like invitations to think more deeply about what it means to be alive in a universe that does not need us, but still includes us. He was not sentimental, but he was not cynical either. He said, the universe doesn't care about us, but that doesn't mean we can't care about each other. It was a quiet ethics, not born from faith, but from understanding. If nothing out there is going to save us, then we must save each other. If the universe is indifferent, then kindness is not trivial. It is essential. This is not science. It is choice. It is how a mind shaped by logic learns to live without certainty and still act with purpose. Hawking did not ask us to believe. He asked us to think, to look at the facts and not flinch, and to still move forward with decency, with cooperation, with humility. In his later years, he became more vocal about global risks, climate collapse, nuclear conflict, unchecked AI. These were not just technical concerns. They were moral ones. He warned that intelligence, without wisdom, was a dangerous combination, that our species' greatest achievements could also be its undoing if we failed to pair power with responsibility. In this, he echoed the old philosophers, those who warned that knowledge must serve something higher than itself, that knowing how must be joined to knowing why, that truth, without compassion, can still destroy. Hawking was not naive. He knew the limits of what science could answer, but he also saw how many of our most urgent problems come not from what we don't know, but from what we refuse to see. Science can measure the rise in temperature, but it cannot make us act. It can simulate global famine, but it cannot feed the hungry. That requires something else. Not intellect, but conscience. Not data, but courage. And in this way, Hawking's philosophy was not abstract. It was lived. He could have retreated. He could have let illness define his identity. Instead, he let questions define it. And through those questions, he reached millions. Not just with answers, but with integrity. He showed what it means to remain curious in the face of collapse, to stay awake even when the body sleeps. That, too, is philosophy. Not the search for immortality, but the cultivation of attention. A refusal to be small just because life is short. A refusal to be cruel just because the universe is cold. A refusal to stop asking just because we may never fully know. His work challenged theologians and comforted the irreligious. Not because he claimed to kill God, he didn't, but because he offered another way to think about meaning without invoking miracles, a way to love the world without imagining it was made just for us. That, in itself, is a kind of reverence. Not worship, but wonder. Not obedience, but responsibility. Not submission to mystery, but companionship with it. He showed us that awe does not belong only to the religious, that physics, when pursued honestly, can be as soul-shaking as scripture. That, to stand at the edge of a black hole and know what happens there, is to face the infinite with nothing in your hands but the strength of your own mind. And somehow, that is enough. Stephen Hawking may never have claimed the title of philosopher, but he earned it, not by pronouncement, but by discipline, by curiosity, by integrity, by refusing to lie about what we do not know, by refusing to stop until we knew just a little more. His life was not only about theories, it was about perspective, about how we stand in the face of scale, uncertainty, and silence, and still speak, still think, still build, still care. And in that posture, we find a new definition of philosophy, not as speculation, but as orientation, a way of moving through reality with eyes open and mind alert. And if Hawking's legacy teaches us anything, it is this: that truth and meaning need not compete, that a cold universe can still host warmth, that the absence of design does not mean the absence of depth, that physics can still leave room for wonder, The final horizon, what remains of Stephen Hawking. There comes a point in every orbit when distance becomes perspective. You've traveled far enough that you can finally see where you've been. The angles shift, the curves resolve, and the shape of the journey appears. Stephen Hawking has reached that point, not in space, but in legacy. His voice is now a memory, but his presence lingers in every equation he shaped, in every question he dared to ask, when silence might have been easier. He left no monument carved in stone, no cathedral, no mountain that bears his name. But he left something larger, a trail of thought woven through black holes, cosmic time, and the fragile places where science meets meaning. It's easy to list his achievements: the singularity theorems, Hawking radiation, the no-boundary proposal, the popularization of cosmology, the fight for science accessibility, the refusal to retreat from public life, even when his own body betrayed him. But what remains, truly remains, is harder to define. It is not found in a textbook. It is not contained in a formula. It is something quieter, a way of thinking, a way of standing in front of the unknown without looking away. He taught us that intelligence does not require mobility. That voice does not require a larynx. That clarity does not depend on comfort. He showed what it means to endure with dignity, to think with honesty, to live with imagination, even when the horizon looks short. And then he extended the horizon. Time was supposed to leave him early. He refused. When he was diagnosed with ALS at 21, doctors gave him only a few years. He lived more than 50, long enough to see his children grow, his books translated into every language, his theories debated by Nobel laureates, long enough to witness a world change because of the words he typed with a single cheek muscle. He didn't escape gravity, but he changed how we understand it. He didn't halt time, but he expanded its definition. He didn't walk through stars, but he drew the maps for those who might. And now that he's gone, what remains? Not the machine, not the lectures, not even the headlines. What remains is the permission he gave to be small and still ask large questions, to be limited and still think beyond limits, to be human and still touch the infinite with thought alone. He reminded us that we are not accidents of matter, we are arrangements of law, that in our brains burn the same patterns that shape galaxies, that the rules of physics do not make us less, they make us real. And that reality, no matter how indifferent, is still worth knowing. He called Earth a fragile cradle. He believed we must leave it one day, not because we are ungrateful, but because the universe is wide. He didn't promise that we would succeed. He only said that we must try, because minds that do not look forward begin to collapse inward. And stagnation, to him, was a kind of death. His own life defied stillness. He traveled without walking, spoke without breathing, taught without standing. He joked, he questioned, he stared down oblivion, and took notes. Not once did he claim to have all the answers, but every time he found one, he used it to ask better questions. That is what science should be, not an end, but a series of open doors, and that is what Hawking gave us, a key to those doors. Even if he didn't walk through all of them himself, he left them ajar for others to follow. So what do we do with what he left? We read, we listen, we calculate, we challenge, but most of all, we wonder. We dare to look into a black hole and ask what it's hiding. We look at the beginning of time and ask what came before. We look at the equations and ask not just what they predict, but what they mean. He reminded us that physics is not cold. It is a search for coherence, for the laws that underlie stars and fingertips, for the structure that makes motion possible and life improbable, but real. And it's not just scientists who can follow him. He spoke to children, to students, to readers on park benches, with no background in science, but plenty of questions. He spoke in simple words about complicated things. Not because he underestimated his audience, but because he respected them. He believed that the mind, no matter where it starts, can stretch to touch the edges of understanding. He believed that every child should look up and see possibility, not a ceiling. He believed that the universe was not ours, but we belonged in it. And that belief was not fantasy. It was physics. Now, the voice is gone. No new books, no revised theories, no surprise appearances, but his words remain, and so does his challenge, not to admire him, but to continue, to keep asking, to keep thinking, to build forward on the ground he helped clear. The future will not remember every detail of his life, but it will remember the shift, the way he changed what it meant to be a scientist in the modern world, not cloistered, not aloof, but public, present, and clear. He gave physics a face that people recognized, and a mind that people trusted, and in doing so, he brought millions into the conversation. He proved that science does not belong to a few. It belongs to anyone willing to listen. And so what remains is not just Hawking the scientist, it is Hawking the signal, the voice that broke through silence, the pattern that persisted through illness, the mind that stayed sharp when the body wouldn't. He showed us how far thought can go when it's not held back by what others think is possible. He showed us that intelligence isn't defined by how fast you move, but by how clearly you see, and he saw clearly through the darkness of singularities, through the fog of probability, through the noise of opinion. He saw structure, and he shared it. Now we walk forward, carrying the questions, carrying the formulas, carrying the quiet conviction that even in a universe that will someday go dark, there is value in lighting a single match and asking what it reveals. That was his final gift. Not a map, but a method. Not an answer, but the courage to seek one. And that remains.